In this video, we're going to talk about acids and bases. First, we're going to look at the definitions, and there is more than one, of acids and bases. Then we're going to distinguish between strong and weak acids and bases and see what makes the difference between them, what causes them to act differently and behave differently. And then we're going to look at the pH scale and the pOH scale and look at how the concentration of hydrogen and hydroxide ions are measured in acid and base solutions. This first slide is actually broader than just this one video. It actually covers the entire module related to acids and bases. In this particular video, we're only going to cover up through 3. So we're going to cover 1, 2, and 3. We'll do the titration experiment in a separate video, and then the buffers most likely in a separate video from that one. Oh, and 6. Just a very brief, at the end of this, we have a very brief review of acid nomenclature, making a distinction between binary and oxyacids. We've talked about this before, but just in case you want a quick refresher on that. There are 2 definitions of acids and bases. The earlier definition was by a Swedish chemist named Svante Arrhenius. His definition was that an acid is any compound that, when dissolved in water, dissociates to produce hydrogen ions. Hydrogen ions. It doesn't matter what the negative ion is. The point was that acids always contain hydrogen ions, and they dissociate to release those hydrogen ions into the water whenever they dissolve. A base is any compound that, when dissolved in water, dissociated into hydroxide ions and then whatever positive ion. Again, here, the positive ion doesn't matter. It's the hydroxide ions. In fact, we're going to see that throughout this, our focus on acids and bases, it will only be the hydrogen ions and the hydroxide ions whose concentrations that we care about. We are going to completely ignore anything attached to either one of these ions. In an acid, we don't care what comes after the hydrogen ion. In a base, we don't care about what comes before the hydroxide ion in the formula. Not as far as concentration. Of course, the identity of the acid or base and whether it's strong or weak will matter to us. But beyond that, the concentration of hydrogen or hydroxide ions are going to be our primary focus. Now, a later definition, which was more broad and more inclusive of more compounds, was the Bronsted-Lowry definition. Bronsted-Lowry actually broadened the definition beyond just hydrogen ion and hydroxide ion producers. Actually, the acid definition is pretty similar, although I think it's a little bit easier to say. An acid is basically a proton donor, which amounts to the same thing. What's a proton? A proton is a hydrogen ion. Most of the hydrogen in our world is hydrogen with only 1 proton in its nucleus and no neutrons. Therefore, a hydrogen ion, which loses 1 electron, will have only 1 single proton. That's why the hydrogen positive 1 ion is referred to as a proton. So a proton donor is a hydrogen positive 1 ion donor. That's what that means. A base, so that's pretty much the same definition. Anything that dissolves in aqueous solution, that dissociates in aqueous solution to donate or to give protons or hydrogen ions. Now, the base definition is broader because it doesn't just say hydroxide ions. A base is a proton acceptor. Anything that accepts a proton by the Bronsted-Lowry definition can be considered a base. Now, this opens up the field to a lot more than just hydroxide ion containing compounds. For example, water, by this definition, can also act as a base. Water can be a basic compound because water can accept a proton and become hydronium ion. And you have seen this ion before. You actually drew this ion when you looked at the different VSEPR examples. One of those examples was the hydronium ion, H3O+. So it had that trigonal pyramidal molecular geometry. So that's a hydronium ion. That is the result of water acting as a base. According to the Bronsted-Lowry definition, water can be a Bronsted-Lowry base and water accepts protons. It accepts hydrogen ions. We're going to refer to hydrogen ions as protons. Sometimes we're going to refer to them as the hydronium ion. It's important for you to remember that every one of these terms means exactly the same thing. They are all synonyms. There's no distinction. The only reason I use one word versus another is just because one view of a hydrogen ion is more relevant to the context than another, that's all. So I'll switch up the terminology. Sometimes I'll say proton or deprotonation or protonation or monoprotic. Sometimes I'll say hydronium ion when I'm referring to water after it's accepted a proton. And sometimes I refer to straight up hydrogen ion. It really just depends on the context, but they all mean the same thing. They are all referring to the same exact species in water. So just some examples of acids and bases. Now we've been looking at acids and bases, and you even learned the nomenclature for acids, so you know how to spot an acid or base. But again, this is part of this is just review, just to cover ground we talked about in module 5, chapter 5, module 5, when we talked about nomenclature. We went over the nomenclature of acids. We distinguished between oxyacids and binary acids. Here we're going to make a further distinction, not in naming, but in strong versus weak. And we're also going to look at some other types of acids, just as a general category. So some examples of acids, of course, you know about hydrochloric acid, begins with an H. Every single acid, and I'm going to try to stick to this as much as possible for your sake. I'm going to try to always draw or write out the acids formulas, starting with the hydrogen, because most of the time that is how you write it. Now, that's not the only way you can write acidic compounds formula. Sometimes they have a more structural type of formula where you write their formula in such a way that the formula resembles their structure. And I'm going to give you an example here, but more or less, even if that's the case, I'm still going to try to start all of my acid formulas with hydrogen, just so you are aware. Any compound other than water and other than hydrogen peroxide that begins with H, where its chemical formula starts with the very first letters, where the very first letter is H for hydrogen, then you can depend on that being an acid. So some examples of acids, we have hydrochloric acid, nitric acid, sulfuric acid, carbonic acid, phosphoric acid, etc. So those are the general formulas. These are what are called inorganic acids. And this is an inorganic chemistry class. General chemistry generally starts with inorganic chemistry. But there is another class of acids called carboxylic acids. These are organic acids. These are carbon-based acids. Now, it's not a huge focus for us, but I just wanted to just sort of introduce you to these other kinds of acids. Their structure is generally some sort of hydrocarbon backbone attached to carbon, oxygen, oxygen, hydrogen. Now, it's not attached. This gives a hint as to the structure, but the real structure is down here. Both of these, all of these examples of carboxylic acids follow this sort of arrangement. The acid part of this is this hydrogen right here is what's called, is your proton. It's the proton that dissociates in water. So in the case of what's called formic acid, the simplest of all carboxylic acids, you have R equal to H. So this is your R value. In this case, it's just H. Then you have the acid portion. This part here is your COOH. This is what this stands for, COOH. That's what it means. It's the COOH is a shorthand for representing a carbon double bonded to oxygen, and that same carbon single bonded to another oxygen, which is single bonded to hydrogen. But this hydrogen over here is your proton. It's the hydrogen that will dissociate. So for example, in formic acid, this hydrogen does not dissociate. It is not an acidic hydrogen. On the other hand, the other hydrogen that's attached directly to the oxygen will dissociate. That is an acidic hydrogen. Hydrogens that are directly attached to a carbon or a nitrogen never dissociate in water. But hydrogens that are attached directly to an oxygen always dissociate in water. Also, hydrogens that are directly attached to a polyatomic ion, generally by way of the oxygen, or to a halogen, hydrogens directly attached to halogens or oxygens that are part of a polyatomic ion, nitrate, sulfate, phosphate, carbonate, etc. Those hydrogens are your acidic hydrogens. Those are your protons. Those are the hydrogens that dissociate in water and become free hydrogen ions. Likewise, you have the acetic acid, normally written as HC2H3O2. Here I've given it its more structurally, the structural formula, or the formula that's more closely tied to its actual structure. In this case, the R group over here represents the CH3. So this R group for acetic acid is the CH3 attached to COOH. And if you add all that up, you get C2H3O2, and then you get the hydrogen out front. So as always, with carboxylic acids, it's that hydrogen that's attached to the oxygen that dissociates in water. Remember, you have your hydrogen bonding, which allows for water to easily remove hydrogens that are attached to oxygens in other molecules. In other words, that hydrogen dissociates to produce hydrogen ions or hydronium ions in solution. So carboxylic acids are a class of acid. Universally, all carboxylic acids, by the way, are weak. And I'm going to repeat that in a couple of slides. You're going to see me repeat a lot of things, just so because I want to drive the point home. There are long hydrocarbon chains. Hydrocarbon chains where it's not just one carbon or a hydrogen, but where R stands for anywhere from 10 carbons all the way to 20 carbons long. Those are generally called fatty acids. Fatty acids, the kinds of fat. When we eat fat, we're consuming fatty acids. And they are basically just long chain. When I say long chain, I mean lots of carbons with a final end of carboxylic acid ending there. So it's a long chain of carbons and hydrogens for the R group. And then at the very tail end, you have a carbon double bond oxygen, single bond OH. You have this sort of trigonal planar arrangement of a carbon with a double bond and two single bonds. Those are called fatty acids, but they're still acids, right? Okay, so Arrhenius bases are all metal hydroxides, calcium hydroxide, sodium hydroxide, potassium hydroxide, barium hydroxide. All of these are metals, metal cations with hydroxide anions. They're all just ionic compounds where the negative ion is a hydroxide ion. And then the positive ion is some sort of metal hydroxide. The only exception is, of course, the usual exception to ionic compounds, ammonium hydroxide would also be included. So ammonium hydroxide is also included with the bases. So ammonium hydroxide would also be an Arrhenius base because when ammonium hydroxide, the ionic compound, dissolves in water, it dissociates to release hydroxide ions, just like any metal hydroxide would. Now, the main class of compounds that are not Arrhenius bases, but are bases according to the broader Bronsted-Lowry definition, ammonia is considered a base by the Bronsted-Lowry definition. And so are all of its derivatives. Now, what's a derivative of ammonia? Ammonia, if you could, well, I hope you recall, this is the molecule ammonia, N with 3 hydrogens attached to it. A derivative of ammonia would replace one or more of those hydrogens with something else. Generally speaking, a carbon-containing piece of the molecule. So for example, an ammonia derivative here might be methylamine. Methyl refers to this CH3 group. Now, this nitrogen is not attached by the hydrogen. It's just a way of writing this. If you really want to see the way the real structure for this methylamine, it would be a nitrogen attached to a carbon, which is bonded to 3 other hydrogens, and then the nitrogen itself is bonded to 2 other hydrogens. So this is a base. Do not confuse all of these hydrogens with hydronium ions or hydrogen ions or protons. These are not the kinds of hydrogens that will ever dissociate in solution. Remember, the hydrogens that are directly attached to carbon or directly attached to nitrogen, except for in the case of what are called conjugate acids, which we'll talk about later. But hydrogens that are part of a base like ammonia or its derivatives are not the kinds of hydrogens that dissociate in water. They remain bonded, covalently bonded to nitrogen. These hydrogens remain covalently bonded to carbon. So when methylamine is dissolved in water, it does not have a tendency to lose hydrogens, but instead it is a Bronsted-Lowry base. And you might ask, well, where's the hydroxide? But a Bronsted-Lowry definition of a base does not require that it release hydroxide ions. Instead, it will act as a what? A proton acceptor. That means if there are protons floating around in the water somewhere, this base will grab on to that proton. And so you'll transform your methylamine into methyl. It will no longer be a free hydrogen floating around, but the nitrogen here will grab onto that hydrogen and will make methylammonium ion. And it'll gain a positive charge. So this is another class of base. Likewise, ammonia, you've seen ammonia and you've seen ammonium ion. The reason you see any kind of ammonium ion is because ammonia is a base. When it gets into the water, if it finds any freely available hydrogen ions, ammonia, the Bronsted-Lowry base, will accept. Another way of saying accepting, accept or take. Maybe it's not accepting, maybe it's not even being offered, right? Maybe it'll just take protons from solution. So ammonia will grab a proton, and once it does, it'll no longer be ammonia plus hydrogen ion, but it'll be one molecule, one polyatomic ion that we call ammonium ion. Ammonium ion. And this would be called, it started off with the name methylamine. It would become methyl ammonium ion, methyl ammonium ion, because there's a methyl group here. Don't worry too much about the naming of methyl. That's organic chemistry. And I'm just showing you this to show you how weak bases actually work. So weak bases can be of two types. Either they are these nitrogen-based bases that are weak bases, or they are insoluble metal hydroxides or insoluble hydroxide compounds, ionic hydroxide compounds that simply don't dissolve very well in water. For example, ferric hydroxide, iron 3 hydroxide does not dissolve in water, or not very well. So it's a very weak base, not because it's not a base, but because it simply doesn't dissolve. So if it doesn't dissolve, that means it doesn't dissociate, which means it doesn't produce enough hydroxide ions to really have a significant effect on the basicity of the solution. Likewise, copper hydroxide does not dissolve in water. Most hydroxides are insoluble in water. The only hydroxides we see that are soluble in water are from group 1 and group 2, the alkali and the alkaline earth metals. Okay, so these are some examples of acids and bases. Now, you are already familiar with this terminology, but I'm going to go over it one more time. Dissociation. You know that dissociation is simply the breaking up of ions in solution. A compound can be a gas or a liquid or a solid outside of water, but that same compound, once it is in water, it can dissolve through dissociating, meaning it'll break up into its component ions. And that's how acids and bases, many of them, work. Certainly the Svante, wrong class of acids and bases. The Svante-Arrhenius acids and bases, they dissociate by, they produce their acids and their hydrogen ions and their hydroxide ions by dissociating. The ions come apart in water. However, in this chapter, unlike the previous chapter where we were interested in the number of ions as a whole and the we use the Van 't Hoff factor to multiply our molarity or our molality, our concentrations by the Van 't Hoff factor as a whole, counting all the ions. In this section, when we talk about acids and bases, now this is extremely important. So if you're doing anything else, please pay attention. Even stop writing right now and just listen. Because if you don't get this, everything about this chapter will become confusing. When we are talking about acids and bases, when we're doing any sort of calculation involving pH or pOH or the concentration of the acid or the base solution, what we are talking about are the hydrogen ions and or the hydroxide ions, and that is all. We do not care about the counter ions. We don't care about the total number of ions of other types of ions. We are going to be laser-like focused on only hydrogen ions and hydroxide ions in this chapter. Those are the only ions that we are going to count. So if a compound, for example, let me give you an example right now, even though I'm going to give you more examples. Let's say you have aluminum hydroxide, which is AlOH3. You know, aluminum hydroxide has 3 hydroxides. The only thing we care about when we dissolve aluminum hydroxide in water, we couldn't care less about the concentration or molarity of aluminum. We don't care. We don't care about the concentration of aluminum hydroxide. We don't care. The only thing we care about is the concentration of the hydroxide ions and how many hydroxide ions will be produced from the dissociation of aluminum hydroxide. So let's say, for example, and I'm going to go over more examples on this. Let's say I have a 2 molar aluminum hydroxide ion. Let's pretend for a second that aluminum hydroxide is a strong base, and we'll talk about that it dissociates completely. Let's say I have a 2 molar aluminum hydroxide solution. The only concentration that is going to be of any interest to me when it comes to talking about acids and bases is the hydroxide ion concentration. I don't care about the 2 molar. The concentration I'm going to be interested in is not going to be 2 molar. Can you guess what it is going to be? What is the actual concentration? What is the molarity I am interested in out of this, this piece of information right here? It's not the aluminum. It's not the number of moles of aluminum per liter. It's not the number of moles of aluminum hydroxide per liter. It is the moles of hydroxide ion per liter. I have a 6 molar. Where did I get 6? Every 2 moles of aluminum hydroxide give me 3 moles. That's 2 times 3 is 6 molar, 6 moles per liter of hydroxide ion. That is the concentration I am going to work with in any calculation involving a base or even an acid. That is the concentration I'm interested in, the concentration of hydroxide ions and the concentration of hydrogen ions. Those are the only 2 ions I am interested in when it comes to acids and bases. The aluminum makes absolutely no difference. In hydrochloric acid, the chloride ion concentration, you know, it's fine if you know it, but frankly, it doesn't matter as far as acids are concerned, because the only ion that matters when you're talking about acids is hydrogen ion. The only ion that matters when you're talking about bases is hydroxide ion. That's it. We're going to count their concentrations. We're going to multiply by a factor that's not the Van 't Hoff factor, but it works similarly in the sense that we are going to look at the dissociated ion and we're going to count ions that are part of a compound. The only difference is we're not going to count all the ions. We're only going to count these 2. We're only going to be interested in these particular counts of ions. Okay, we're going to do more examples of this. This is not the last you've seen of this. So if you don't take this concept, if you don't really get used to this concept, this entire chapter will just seem like a mystery. And why we keep coming up with numbers that are different from the molarities will just be a continuous mystery unless you accept this fact. Okay. Okay, so I've already mentioned that the hydronium ion, H3O plus, is the same as the hydrogen ion, which is the same as the word proton. And I'm just going to use them. And I explained why we say the word protons, because 99% of the hydrogen on Earth is protium isotope, which means it has no neutrons, which means that once the hydrogen atom loses an electron to become H plus 1, the only particle that's really left is a proton. A hydrogen ion is really just a free-floating proton. So you know what protons taste like. Protons taste sour. You know the taste of a fundamental subatomic particle. Whenever you taste something sour, you're generally tasting protons. You're tasting because acids tend to be sour. Acetic acid, citric acid, ascorbic acid. Everything that tastes sour to you, generally speaking, is an acid. Orange juice is loaded with citric acid. And it's got ascorbic acid as well. But that sour flavor comes from the free-floating protons in solution. So you know what protons taste like. You know the taste of a subatomic particle. You also know what hydroxide ions taste like. They taste bitter. Sour is associated with acids. Bitter flavor is associated with bases. That's because a lot of poisons in nature are what are called alkaloids, meaning they are basic compounds. They are compounds that contain a lot of nitrogen bonded to a lot of carbons. They tend to be bases, and as a side product, they tend to generate some hydroxide ion as well. So the point is this: the reason things that taste bitter are basic is because a lot of basic compounds in nature are actually poisonous to us. And the bitter flavor is actually meant to warn us away from those flavors, but instead we drink them up as coffee. So go figure. And I mentioned this here, so just again, generally only hydrogens and acids that are directly connected to an oxygen or a halogen are protons. Hydrogens bonded to carbon never dissociate. Hydrogens directly bonded to a carbon never dissociate. So all of those hydrocarbons where we have C3H8 or octane C8H18, those 18 hydrogens and those 8 hydrogens, they are not acidic. These are not acids. So be careful about that. Acids are very special compounds that have a hydrogen either bonded to, actually, let me make it more broad than that. Hydrogen bonded to a very electronegative element, either oxygen or one of the halogens. Yet for some reason, not nitrogen. That's because nitrogen is just a different kind of atom, and instead of letting go of its hydrogens, it actually grabs more hydrogens. That's because it has a lone pair that is eager to bond hydrogens. Okay. So for example, the 3 hydrogens in the acetate ion, these 3 hydrogens right here, even though acetic acid or acetate ion is part of an acid, it's not those 3 hydrogens. I can't draw, okay. It's not those 3 hydrogens. Those 3 hydrogens are attached to one of the carbons. It's only the hydrogen, as you saw earlier, back over here. Where is it? Back over here, when you look at acetic acid, it's only this hydrogen. If this is acetic acid, then this is CH3, C2H3O2 hydrogen. It's only this hydrogen that is your proton, that is your hydrogen that's going to dissociate in water. The other 3 hydrogens that are connected directly to carbon, they do not dissociate. That is not part of what an acid is. I want to make that clear. Acids are very specific types of compounds. Not just anything with a hydrogen can be an acid. Hydrocarbons have lots of hydrogens, not one of them. Not one single acid in a simple hydrocarbon bonded to carbon, where hydrogens are all bonded to carbon, is going to act as an acid. Now, if the hydrogen is bonded to an oxygen, which is bonded to a carbon, that of course is completely different. Then you have an acidic hydrogen. In fact, anytime you see a hydrogen bonded to an oxygen, chances are that hydrogen can act as an acid. And if it's ever not the case, I'll warn you. Okay, here's that same formula again, that same layout for what a carboxylic acid is. Here's the same discussion again about formic acid. Yeah, I'm a little redundant in this one. I just want you to get the point really badly. That's all. There are a lot of little fine detailed points here that I feel are worth repeating. Again, this is just more of a review. Terminology, we have oxyacids and binary acids. Remember when we talked about nomenclature, oxyacids were when when hydrogen ions were bonded to polyatomic ions that contained oxygen. So for example, hydrogen nitride is nitrous acid. We have chloric acid, hydrogen bonded to the oxygen-containing polyatomic ion chlorate, and so on. All of your carboxylic acids, these organic acids, are also oxyacids because they all involve a hydrogen bonded to an oxygen, which is then bonded to a carbon. But again, the point is that the hydrogen is directly connected to an oxygen. This hydrogen is not acidic. The one that's connected directly to the carbon is not the acidic hydrogen. It's the hydrogen that is directly connected. It's the red one. It's the one that's directly connected to the oxygen. That's your acid hydrogen. Binary acids, if you recall, are when the hydrogen are attached to a negative ion that does not contain oxygen, including cyanide, which is a polyatomic ion as well, but the cyanide ion does not contain oxygen, so it is part of the binary class of ions. Hydrofluoric acid, hydrochloric acid, all the halogen acids, HF, HCl, HBr, HI, these are all binary acids. And remember, there was a difference in naming these as well. You use the prefix hydro for binary acids, and you use no hydro prefix for oxyacids, but instead you name the acid, you give it a special ending of OUS or IC, depending on what kind of polyatomic ion the hydrogen is attached to. If the polyatomic ion has a name that ends with 8, like hydrogen chlorate, it becomes chloric acid. If it ends with if the hydrogen is attached to a polyatomic ion whose name ends with ite, like hydrogen nitrite, you end the acid name with us acid, nitrous acid. Nitric acid would be hydrogen nitrate, HNO3. HNO2 is nitrite, nitrous acid. Us from ite gives you us acid. 8 gives you ic acid. Remember, we've talked about this nomenclature before. Make sure you haven't forgotten it and review it. And I have a slide here at the very end of this, which also reviews these same rules that I'm going over with you right now. And that's it. That's the entire nomenclature for acids. Knowing the difference between oxyacids and binary acids, knowing when to use the prefix hydro and when not to use the prefix hydro, and knowing which polyatomic name ending turns into ic acid and which one turns into us acid, OUS acid. Amphoteric, the word amphoteric means that a compound can act as both an acid or a base depending on situation. Water is the ultimate example of an amphoteric compound. Water can be an acid and act as an acid and donate away one of its protons, or it can act as a base, and we already saw this, water can act as a base and take a proton or accept a proton. So we saw water acting as a base already, right? Water can accept a free-floating proton and become hydronium ion, H3O+. How does water act that's water acting as a base, taking a proton. How does water act as an acid? Well, what do acids do? They donate protons. Water can give away one of its protons. Water can say, here, take a hydrogen on me. Go ahead and take my hydrogen. Well, once it does that, what's left? That results in what's left is, let me keep the color coding, sorry. That results in HO with a negative charge because water just lost one of its positively charged hydrogens, and the hydrogen goes off all by itself as an H+ ion, a free H+ ion, or probably an H+ ion that is now attached to something else that was a base. So you have hydroxide ion. And later on, we're going to have a special name for this. We're going to call hydroxide ion the conjugate base of water when it acts like an acid. And we're going to call hydronium ion, H3O plus, the conjugate acid of water when it acts as a base. Anyway, so that's what happens to water. When it acts like an acid and donates its proton or one of its protons, and it can only donate one of its protons. It's never going to donate the second one. But when it donates one of its protons, what you have left is hydroxide ion, the ultimate base ion, right? Water acts as an acid or a base. But it's not the only compound that can do that. Most of the time, other compounds that do act like that tend to become, well, I shouldn't say tend to become, other compounds that can do that, they tend to be ions. Yeah, they do tend to be ions. So a lot of what are called diprotic acids, once they've lost their first proton, once they've undergone their first deprotonation, they tend to become amphoteric compounds or amphoteric ions, meaning they can either regain a proton, thus accepting a proton, or they can lose yet another proton, acting as proton donors or acids. So deprotonated polyprotic acids is how you say that. A partially deprotonated polyprotic acid can also be amphoteric. So water and other compounds can be amphoteric, acting as either an acid or base depending on circumstance. They can do both. They can go both ways. All right. Some more terminology. I thought I had some more terminology here related to polyprotic, monoprotic. Okay, well, let me just go over some terms before we go on to the next slide, which is a good one to look at, some good terminology here. Let me just, I thought I had another slide about some more, I thought I had some more terminology here. I guess I don't. I guess I don't. Okay. Well, let me just define a couple of other terms. You'll get what I'm saying just from the, by repeated use, you'll probably understand what I'm saying, but let me just make sure I explain it. I'm going to use a lot of terminology here. Monoprotic acid. Mono means one, right? Protic means proton. It's an adjective. So what I'm saying when I say a monoprotic acid, it's an acid that only contains one hydrogen ion in its formula. For example, HCl, HBr, etc. A diprotic acid, diprotic, has two hydrogens, H2CO3, H2SO4. These are examples of diprotic acid. Triprotic acid, there aren't too many of those. Triprotic, phosphoric acid, for example, is triprotic. Triprotic, di means two hydrogens, tri means three hydrogens. So phosphoric acid, phosphorus acid, etc. These are triprotic. Or another word is polyprotic. Polyprotic acids are just acids with more than one hydrogen ion. That's all they are. Polyprotic just means the acid has more than one hydrogen ion. So a diprotic or a triprotic acid is a polyprotic acid. Poly means many, protic refers to the number of protons in the acid's formula. Again, only protons. So having a bunch of hydrogens connected to carbon, that doesn't count as polyprotic. It's only the number of protons. I mean, when I say protons, I mean specifically the number of hydrogen ions that are going to dissociate if that compound dissolves in water or enters into the water to make a solution. Another term I use is protonation and deprotonation. Protonation. Protonation just means when you add hydrogen ion to something. So for example, when a base like ammonia undergoes protonation, when a hydrogen gets stuck onto this, that's called protonation. It just means you've added a proton to something or added one more proton to something that didn't have that proton before. It's the act of adding a proton to something. It's called protonation. Deprotonation, I think you can probably guess, right? H2O becoming hydroxide ion. That's the loss of a proton, so that's called deprotonation. D, undoing it, removing a proton, removing a proton from something that originally had one. Protonation is adding a proton. And you can have multiple protonations. You can have the first deprotonation, second deprotonation, etc. If an acid, if a triprotic acid like phosphoric acid, it can undergo up to 3 deprotonations. You have your first deprotonation, which would give you your second deprotonation. Deprotonation would give you hydrogen phosphate or biphosphate with a 2- charge. Finally, the last deprotonation of this would result, can undergo its first deprotonation to become bisulfate ion or hydrogen sulfate ion. And then its second deprotonation would result in just sulfate ion, etc. So acids can undergo, polyprotic acids, acids with more than one possible proton to be lost, can undergo multiple deprotonations. There aren't a lot of examples of protonations, multiple protonations of bases. Generally, you can only do one. It's very rare that you have more than one basic proton accepting atom in a molecule. Another term, I don't use this as much, but you will see me use it in one of the upcoming examples, monobasic, dibasic, and tribasic. So monobasic, having only one hydroxide ion in the formula. So for example, sodium hydroxide is monobasic. Potassium hydroxide, monobasic, because there's only one hydroxide. Well, what's the alternative? The alternative would be to have a dibasic or a tribasic. Dibasic examples would be calcium hydroxide, barium hydroxide, copper 2 hydroxide, etc. These would be dibasic. Tribasic, not too many of those. There are a few. We have aluminum hydride. Again, tribasic, it has 3 hydroxides. The word basic here is referring to the number of hydroxide ions. So it's kind of the opposite of diprotic, monoprotic, and triprotic. You have dibasic, monobasic, and tribasic. It's sort of the base equivalent of those. For some reason, I had a slide that detailed that terminology, but I guess I had these laid out somewhere. Okay, well, sorry about that. Here it is. Well, here it is, handwritten. Anyway, I think you get the idea. And I'm going to use this terminology a lot, and I'm going to usually explain what I mean. It looked like it was here, right? I mean, I'm using the terminology. Huh, okay. Okay, now let's talk about equilibrium and whatever this other word is, reversibility. We've talked about this before, actually. We have talked about equilibrium and reversibility. Some processes and some chemical reactions and some dissociations are reversible. And we use, to display that, by the way, we use these equilibrium arrows, these double-headed equilibrium arrows. They basically point in the so-called forward direction, left to right, and the reverse direction, right to left. Microscopic reversibility. Now that sounds all very fancy and all, but microscopic really doesn't say much here. Reversibility is the point. Some reactions and some processes are examples, and you'll see exactly what I mean. For example, the decomposition of carbonic acid or hydrogen carbonate is reversible. Remember, carbonates decompose into carbon dioxide and then whatever the oxide is of the positive ion. In the case of carbonic acid, the positive ion was hydrogen, so its oxide is water. An oxide of hydrogen is water. So this decomposes, but this decomposition is reversible, meaning if I blow a bunch of CO2 from my own breath into water through a straw, I will actually reform carbonic acid, and I've done this. And I saw the results because I can actually change the color of a solution that has what's called an acid-base indicator in it. I had an indicator, it was called bromthiamyl blue, or thymol blue, I forgot which one it was, but it's a blue color. It changes to yellow in the presence of an acid. So I took a straw and I blew into the solution, which was just plain water and this acid-base indicator. After blowing into the solution just for a few minutes, the solution turned bright yellow. And that's because the carbon dioxide from my breath, whenever you exhale carbon dioxide, mixed with the water and formed carbonic acid, and the acid-base indicator picked up on that, saw it, and changed color to yellow because it changes color whenever there's an acid around. So you can make a plain pure water, you can turn pure water acidic simply by blowing air into it, because your breath contains carbon dioxide as well as water vapor. There's another process involving carbonic acid that is also reversible. This is not a chemical reaction, but it's the dissociation. The dissociation is not a chemical reaction. This one is a decomposition. So carbonic acid can undergo two different processes, and in fact, it does undergo two different processes, both in your blood and in the earth. It can decompose or it can dissociate. Once H2CO3 is in water, it'll actually dissociate. It'll decompose into water, but once it's in more water, it can dissociate into protons because it is an acid, carbonic acid, and bicarbonate ion. You've heard of bicarbonate ion. It's a part of, what is that? Baking soda. Sodium bicarbonate. Anyway, bicarbonic acid can dissociate into hydrogen ions, protons, and into bicarbonate. This is a reversible process. Reversible processes are a feature of what are called weak acids. Only weak acids only have reversible dissociations among acids, and only weak bases have reversible dissociations as well. Only weak acids and bases are reversible. Their dissociation process is reversible, meaning the hydrogen can reconnect to the bicarbonate, and reform and go work backwards and reform hydrogen carbonate or aqueous carbonic acid. This reaction, or this dissociation, let's be clear, it's not a chemical reaction. This dissociation can occur in both directions, the forward direction and the reverse direction. It goes both ways. And the very important part we'll see later when we talk about buffers, the thing that makes this so critical and so important to us, our lives literally depend on carbonic acid's ability to do this, by the way. Our lives depend on it. It's happening right now in your bloodstream. The thing that makes this so important is that it is reversible. This is in response to whatever the environment is doing. This process will respond as if it's alive. It will respond to changes in the outside environment. If you try to tamper with equilibrium, the equilibrium system, that is this reversible system, will react as if it's a living thing. It will respond. In fact, you can almost consider living things to be nothing more than a very fancy version or very fancy collection. So what is equilibrium? Well, you know what equilibrium is, but let's talk about it some more. Equilibrium is just a reversible process that happens to have the forward rate and the reverse rate equal to each other. So it has both the forward process and the reverse process occurring simultaneously at equal rates, so that there is no net change between the left side of the double-headed arrow and the right side of the double-headed arrow. Yet the process is continuing even though you can't see any change. So for example, at equilibrium, carbonic acid is dissociating to produce hydrogen ions and bicarbonate ions constantly. But elsewhere in the solution, protons and bicarbonate ions are coming together and reforming carbonic acid molecules. And both of these processes, these are counteracting each other exactly. They are both happening at the same time, maybe not necessarily to the same molecule, maybe in different places throughout the volume of the solution. But they're both happening simultaneously and at the same rate. So every time one carbonic acid dissociates, another proton and bicarbonate ion get together and produce a carbonic acid molecule all over again. So there is no net change. If you're simply looking at the values or the concentrations of carbonic acid, hydrogen ion, and bicarbonate, you will not see any change in their concentrations or the number of each of those ions and molecules. But they are constantly undergoing creation and destruction. Carbonic acid is constantly being broken down and then reformed at the same rate. Protons keep appearing and then recombining to bicarbonate with bicarbonate and disappearing. Everything keeps happening, but they're all counteracting each other. It seems like a worthless process, right? It seems like it's just a big waste of energy. But it's actually very important, because what that means is that anything that tries to disturb equilibrium, equilibrium is already involved. It's already dynamic. It's already moving and mobilized, ready to counteract anything you try to do to disturb equilibrium. If you try to add more carbonic acid into the solution than equilibrium has decided is the right amount, equilibrium will shift into high gear. It will shift rightward and will take that extra carbonic acid and break it down into protons and bicarbonate ion. That's what equilibrium does. It fixes the quantities, their relative ratios, in a constant, literally a constant ratio. If you try to do anything to disturb equilibrium, it counteracts what you do. This is referred to as Le Chatelier's principle. Le Chatelier, a French, I don't know what he was. If he was I don't know if they called him chemists at that time, but French natural philosopher, maybe, scientist, whatever. Le Chatelier's principle. Le Chatelier basically said that anything you try to do to disturb a system that is in equilibrium, the system will counteract anything you're doing. If you try to add more of one compound, like say, for example, you put a bunch of protons into the solution that were not there naturally by equilibrium, the system will respond by doing the reverse, by combining those new protons with bicarbonate ion to make more carbonic acid. They will lock up the protons. If you put more carbonic acid in, it will take that carbonic acid and it will turn it into, it'll break it down into protons and into bicarbonate ion. Whatever you do, the system opposes it. Now, the next part here is a little bit more advanced. It's kind of beyond the scope of this class, so I'm not going to really go into it too much. I've placed this here mainly for your notes. So this is sort of optional. If you really want to know more about the details of equilibrium and the equilibrium constant, go ahead and read up on this. I'm not going to spend any extra time on this. It really is more detail than you need for anything in this class. But this is for your own curiosity. This is totally optional material for you. Bottom line is, this K value here is the constant I'm talking about. It is the constant that dictates the ratio of products of some given aqueous product to the given aqueous reactants. There's a ratio established by nature, and we call that fixed and constant ratio. We give it the letter or the letter designation, lowercase k. So K stands for constant, and it's the equilibrium constant. Every reversible reaction has an equilibrium constant K associated with it for a given temperature, by the way, for a given temperature. K is different values for different temperatures, but temperature is the only thing that changes the value of K. Now, the only thing we need to know, or the only relevance this has to our discussion, hold on one second. Just give me a second here. Give me 1 second. Okay. Okay, all right. Here we are. I hope that you can't hear that. That's my printer doing something. I don't know what. It's not printing, it's doing something else. Okay. The equilibrium constant Kw for water what happened? Here it is. So all of this stuff is to say that the equilibrium constant for water is the product, is the multiplication of hydrogen ions in solution and hydroxide ions in solution. This is the Kw value for water. The W just stands for water. This is just a special, it's no different from any other reversible processes equilibrium constant, but at equilibrium at 25 degrees Celsius specifically, the products of the auto-dissociation of water are measured, and it was measured at 1 × 10⁻⁴. Now that number is going to become important to us. And you should probably memorize 10⁻⁴. What that means is that water has this auto-dissociation tendency. What does that mean, auto-dissociation? Auto-dissociation is when water all by itself, without any other chemical acting on it, in water, pure water at 25 degrees Celsius will dissociate all by itself, not even without any help from another chemical, into hydrogen ions and hydroxide ions. So when you drink, if you ever drink a cup of pure distilled water, or even any kind of cup of water, you are drinking both hydrogen ions and hydroxide ions, as well as the intact molecule. And that's no big deal, right? So there's 2 ways to see this, by the way. One, you can see this as H2O breaking down or dissociating to H plus and OH minus, or you can see this another way. Both of these, by the way, both of these ways of seeing this are completely and perfectly valid and interchangeable. It really is just a matter of your preference. Another way to see this is that one water molecule bumps into another, and as a result, one of the water molecules takes, yeah, I'll draw it from the oxygen because it's the oxygen that's doing the taking. One water molecule acts as the base and the other water molecule acts as the acid. Remember, I said water is amphoteric? Well, here's a good illustration of that. One water molecule will become the base, the other will become the acid. The base will take a proton from the water that is acting as an acid, which will give or donate its proton, and you'll end up with one water as H3O plus hydronium ion, and the other water that lost its hydroxide ion will become hydroxide ion. Well, that lost its hydrogen ion will become hydroxide ion. Okay, I'm trying to draw Lewis dot structures, but clearly it's not working here. Okay, Nice dots there. All right. So that's another, these are two exactly equivalent ways of seeing this. Both of them tell you the same story. They tell it to you in slightly different ways, but more or less this is the story. Either way, you're getting positive hydronium ions or acid ions and negative base ions in water at 25 degrees Celsius. This happens at a rate that is equivalent to a constant where Kw equals 10 to the negative 14. That is an extremely small number. That is 1 out of every quadrillion water molecules. So this is not very common at all. Okay, so this doesn't happen much. For the most part, you're drinking plain old water molecules. But, you know, you do get a few ions. Out of 1 out of every however many trillion, quadrillion molecules, you're going to get a hydrogen ion or a hydronium ion and a hydroxide ion. So however you see this, that's what happens. So this number is important because this becomes the definition. This equilibrium constant Kw is the basis for our definition of the pH scale. Now, what does water have to do with pH and acids and bases? Acids and bases cannot exist outside of water. There is no such thing as a solid or a liquid acid or base. For example, hydrochloric acid is actually a gas at room temperature. It's hydrogen chloride when it's a gas. It doesn't become an acid. It doesn't become an acid until it dissociates, and it doesn't dissociate until it enters the water and then breaks up and dissociates into hydrogen ions in water. Outside of the water, hydrogen chloride is a molecule. It's a gaseous state molecule, but it's not because it's a gas. Take, for example, nitric acid. It's not it's hydrogen nitrate. It's a liquid molecular compound when there's no water nearby. If you have anhydrous hydrogen nitrate compound, it is a pure viscous liquid, and it has absolutely zero acidity. That's because without water, the hydrogen ions are not going to dissociate. Liquids don't typically dissociate to any appreciable degree. I mean, look at water. Water dissociates 10 to the negative 14. What is that number, by the way? That's a decimal with 13. I have it written somewhere else, but I'll do it here. 3, 6, 9, 12, 13. 13 zeros and a 1. That is the molarity of hydrogen. Sorry, not the molarity. Excuse me. We'll talk about molarity in a second. That is the dissociation rate of water. So it's 1 out of every, what is that? Hundreds, millions, billions, trillions, like 1 out of every 10 quadrillion molecules, you're going to see some ions, right? That's it. Or 1 out of every 10 quadrillion molecules will dissociate. That's hardly anything. And that's true of a lot of liquids, a lot of molecular compounds that could be acids. They're not going to deprotonate themselves. They have to be in water. Okay. So the products of water's dissociation, and again, I use the word product here loosely, we mean the dissociation products, are hydrogen ion and hydroxide ion. The square brackets, by the way, over here, these square brackets, whenever we use square brackets in this context, the square brackets mean the molarity of whatever's inside the brackets. So when I put square bracket H plus, what I'm saying is that is the same as saying, oh, what is, or that is the molarity of hydrogen ion. Square bracket hydroxide means the molarity of hydroxide. Molarity of hydroxide, meaning how many moles of that ion per liter of solution. You can do this with anything, by the way. The molarity of, for example, copper sulfate, it's not typically used for any other kind of compound, but you could say molarity of copper sulfate, brackets copper sulfate. We are not going to use this for anything except hydroxide and hydrogen ions. So. Okay, so let's go here. Okay, so our discussion about reversibility and equilibrium brings us to a discussion or the distinction between weak and strong acids and bases. I think I've already hinted at it that weak acids and weak bases are the only kinds of acids and bases that undergo a reversible process. Their dissociation is reversible. Acids and bases can be either strong or weak, and it has nothing to do with their concentration. And by the way, it has nothing to do with pH necessarily either. I mean, it's related, but it's not the same thing. And we'll take a look at, we'll actually do an example where I really illustrate that point. A strong acid is a strong electrolyte. So electrolytes, remember, were compounds that dissociated into ions completely when they entered the water. Strong acids dissociate 100%. The best example, hydrochloric acid, strong acid, 100% deprotonation. By the way, dissociation and deprotonation in this context, for our first deprotonation, means the same thing. So 100% deprotonation or dissociation of the hydrogen ion. A deprotonation is simply a specific kind of dissociation where you're talking specifically about an acid dissociating its hydrogen ion. So 100% dissociation means that every single hydrogen chloride that enters the water will produce one hydrogen ion and one chloride ion. Therefore, if we have 5 molar hydrochloric acid, we have 5 molar hydrogen ion and 5 molar chloride ion. We have 5 molar concentrations of each of the ions. Now, if that sort of bugs you, just recall, this is chemistry. The arrow is not an equal sign. We are not saying 5 equals 5 plus 5. We're saying 5 molar hydrochloric acid will dissociate to yield 5 molar concentration hydrogen ion and 5 molar chloride ion. This is not 5 plus 5 equals 5. This is 5 yields 5 of each thing that made up the original hydrochloric acid. So be careful about that idea. Don't cut it in half. Oh, and here's the other example. Here I use 1 molar. Same thing though. 1 molar of hydrochloric acid will produce a 1 molar solution of hydrogen ion and a 1 molar solution of chloride ions. Exactly the same concentration because 100% of the HCl is converted into H and Cl minus. How much hydrogen chloride molecule is left intact? Undissociated molecule is left in the water after it dissociates? None. 0 HCl, 0 actual molecular hydrogen chloride is left in the water because all of it has been converted into free-floating dissociated ions. So its Van 't Hoff factor is 2. Not that we're going to be using Van 't Hoff factor for the purpose of counting all the ions. We're only going to care about the hydrogen ion, but just to let you know, it is a perfect 2. It's a perfect dissociation. I'm saying all this to distinguish this from weak acids. Weak acids do not act as expected. Weak acids have reversible dissociations. They establish an equilibrium, and this is what makes weak acids so much more useful to us. You may think strong is great, strong is always the best thing, right? No, it's actually weak acids and weak bases that are the most important compounds for us. Strong acids actually do very little for us. Other than helping to digest our food, we really don't have we don't have a lot of use for strong acids. The only place we have strong acids in our bodies are the hydrochloric acid in our stomachs. That's it. And even that doesn't digest the food. It just loosens it up. It just denatures the proteins in our food. It doesn't actually digest them. We actually use enzymes for that. Anyway, some people have this idea that acids somehow dissolve proteins or dissolve food in your stomach. They do not do that. That is not what an acid can do. It's way beyond an acid to do that. Anyway, so weak acids have reversible dissociations and thus dissociate to a very limited extent, usually much less than 1%. Usually much less than 1% of the moles of a weak acid or a weak base that enter the water will actually dissociate into hydrogen ions or hydroxide ions, respectively. Very limited. I'll give you some numbers that are kind of made up only for the purpose of examples. Their real dissociation factors are actually so low that it would actually make very little sense for me to try and give you an example with actual numerical values. So I kind of use like 1% or 5% rather than the 0.00001% that they actually do dissociate. A weak acid will not produce that many moles of hydrogen ions as the number of moles of acid. So, for example, taking the same acid, hydrogen fluoride or hydrofluoric acid is a weak acid. By the way, I'm going to give you a list of strong acids to memorize. It's going to be a very short list. Hydrofluoric acid is a weak acid. When 1 mole of hydrofluoric acid is added to water, this is an exaggeration, but it's about right. Only 0.01 moles of hydrogen ions and 0.01 moles of fluoride ions are produced. The other 99.99 moles are intact, undissociated, perfectly covalently bonded hydrogen fluoride molecules. So 99.99 moles will remain unaffected of hydrogen fluoride, will remain undissociated. They'll still dissolve in the water, but they'll dissolve through the typical dipole-dipole, hydrogen bonding type dipoles, not by dissociating. Remember, acids are molecules, so they can dissociate, they can dissolve in more than one way. Okay, so only a tiny fraction of a weak acid will actually dissociate. Most of it will remain intact. So once dissolved, there will be 3 different species of things in solution, of dissolved particles in solution for a weak acid. You'll have the intact molecular acid, in this case, hydrogen fluoride. Then you'll have hydrogen ions, and then you'll have the counter ion, fluoride ion, in this case, fluoride ion, or whatever the counter ion is for that acid. The Van 't Hoff factor for I, or the Van 't Hoff factor I for HF then would be approximately 1. 1 because you've got dissolved molecules, slightly higher because you've got a little bit of hydrogen, excess hydrogen fluoride ions, so you got a little extra in there. Some of those hydrogen fluorides broke up into 2 particles, so you've got maybe 1.02 instead of exactly 1, because some of your dissolved particles actually did break up into more particles. So you don't get as many moles of dissolved particles as you should get by that, or as you would expect from simply looking at the formula, because there isn't perfect association. Weak acids, strong acids associate one of how many hydrogen ions it can dissociate relative to the number of acid molecules. If it's a 1-to-1 ratio of hydrogen ions to molecules, or greater than 1, then it's a strong acid. If it's less than 1, then it's a weak acid. Bases are measured in exactly the same thing, only with reference to hydroxide ion. For example, a 1 molar sodium hydroxide solution will have a concentration of 1 molar hydroxide ions and 1 molar sodium ions. This is 100% dissociation. There will be zero sodium hydroxide intact left over, meaning there will be no compound known as sodium hydroxide sinking to the bottom of the beaker of water. No, all of it will dissociate. However, a weak base, like say, for example, magnesium hydroxide, which doesn't really dissociate that well in water, will produce far less moles, fewer moles of hydroxide ion and magnesium ion than the expected amount. And there will be plenty of undissolved, in fact, solid, undissolved and undissociated magnesium hydroxide. If you try to add magnesium hydroxide to water at a temperature that it's not very soluble at, you'll actually see that the magnesium hydroxide doesn't dissolve, or it'll barely dissolve. It won't even be noticeable. So little of it dissolves. So for this, its Van 't Hoff factor is approximately 1, as if it's a molecule. It's not a molecule, though. It's just not dissolving. It's remaining solid. Unlike a molecule, though, ionic compounds cannot dissolve in any other way but by dissociation. So it'll look like a solid. When ionic compounds don't dissolve, it's very obvious because they remain solid. When molecular compounds don't dissociate, they can still dissolve, in which case you can't see them anymore because they're dissolved. And here's yet another reminder that we are only going to be focused on hydrogen ions and hydroxide ions. Okay, let's see. There was one other thing I thought I wanted to mention here. It'll probably be covered in the examples. I just want to, I felt like there was something on the tip of my tongue I wanted to mention. One more thing. Dissociate completely, hydrofluoric. We'll get to it. We will get to it anyway, one way or the other. Okay, now this is our strong acids and strong bases list. It is not a very hard list to memorize. There are only 6 items. Let's see. There are only 6 strong acids. The strong bases actually can, I recommend you memorize them by group. All the metal hydroxides from group 1, in other words, sodium, lithium, potassium, rubidium, cesium, all the hydroxide compounds that you can make from group 1 metals, and all the group 2 hydroxides starting about halfway down. So not beryllium and not magnesium. So these 2 are out for group 2. For column 2, these 2 are out. But for the rest of column 2, halfway down column 2 and onward, the rest of column 2, all those metal hydroxides, calcium, strontium, barium, we probably won't go much lower than that. These are all strong. So it's basically 1.5 columns, 1.5 columns. The first 1.5 columns, of the periodic table, metal, M for metal, hydroxides. Those are your strong bases. Metal hydroxides from column 1 or halfway down column 2. Calcium, strontium, barium. For the acids, hydrochloric acid, you've heard of that, that's our stomach acid. The rest of the halogens also make strong acids. So chloride, bromide, iodide, everything except all the halogens except fluorine. So fluorine does not make for a strong acid. It's the only halogen that is not a strong acid. Sulfuric acid, it sounds strong, doesn't it? It's battery acid. Nitric acid, strong acid. The 2 higher oxidized versions of the oxychlorine family. The chloric acid and perchloric acid, those are strong acids, but not the lighter ones, not the, when I say lighter, I mean, not the ones with less oxygen, not the chlorous acid or the hypochlorous acid. In fact, if you look at this list, no acids, right? All of these are ic acids, right? Now that doesn't, I'm not trying to say that all, like phosphoric acid, for example, is not a strong acid. Carbonic acid is not a strong acid, but at least don't pick anything that has that's like nitrous acid or sulfurous acid or chlorous acid or hypochlorous acid, etc. Only at the very least, if you see those, you know that those are weak acids. Anything not on this list you can go ahead and just assume it's a weak acid or a weak base. If it's not on this list, it's weak. So for this list of strong acids and strong bases, as far as we're concerned in this class, this is the entire list. There are other strong acids and bases in the world, but these are the ones that you're gonna run into most of all. Most acids in the world are weak. Most bases in the world are weak. It's a very short list. It's not exhaustive, but this is most of them. In fact, probably the only ones you're ever likely to hear of other than like the super acids. Like antimony pentafluoride dihydrofluorine or something. That's a super acid though. That's extremely unusual. So you're not gonna see anything like that. And I'm not going to ask you anything like that, of course, about that. But anyway, just to help you out, and also because I want you to understand as much about chemistry as you can, ammonia, remember, and its derivatives are always weak bases. These so-called Bronsted-Lowry definition type bases are weak. Now, that's not to say the metal hydroxides aren't also Bronsted-Lowry. They are. But these, I point out, these ammonia and ammonia derivatives are bases by definition only by the later Bronsted-Lowry definition that came along. That's why I specifically call them that. But all carboxylic acids, meaning all those acids that have this form or have this form, are weak. Also, actually, in the general rules, any acid containing carbon is weak. So that also includes a non-organic carbon containing acid. Carbonic acid is also weak. Even though it's an ic acid, it's weak. So all carbon containing acids, carbonic acid is weak, acetic acid, which is just a type of carboxylic acid, is weak. Any carbon, if you see carbon in the formula, you know for sure it's a weak acid. If you see carbon in the formula, it's probably also, if it's a base, it's probably also a weak base. So if you see carbon, it's weak. There are no examples of strong acids or bases that involve carbons. It's one of the few rules I think there are no exceptions to. So you have six of them in no particular order, 7, sorry, 7, 1, 2, 3, 4, 5, 6, oh, I'm sorry, 7. I added the perchloric acid. I didn't used to say this, but now I do. I noticed other instructors say it, so I started saying it too. I wanted to keep the list short, but if others are going to expect you to know this, then I should expect you to know it too. But that's it. I don't think there's anything else. Okay. See, that's about all I had to say there. Again, this is more stuff about the auto-dissociation of water. I guess this is repetitive. I repeat these things multiple times because I think it's important and I want you not to miss the idea. And it's very easy to miss the idea. So here again, this is all a repeat. In fact, this entire slide is redundant. It's just slightly more detail. We have the auto-dissociation constant for water at 25 degrees Celsius. This is the basis. Auto-dissociation of water and this dissociation constant for water specifically at the temperature 25 degrees Celsius is the basis for the pH scale. That's why I mention it again here. So the product of hydrogen ions and hydroxide ions, not just in water, but in water or in any aqueous solution, any aqueous solution at all, this is going to be the case where the hydrogen ions multiplied by the hydroxide ions are going to equal 10 to the negative 14 at 25 degrees Celsius. And for the purposes of this class, we're always going to assume room temperature. I'm not going to mention it. You're just going to assume room temperature. The auto-dissociation of water is an endothermic process. What that means is if you add more heat, if you raise the temperature above 25 degrees Celsius, you actually get more hydrogen ion and more hydroxide ion, and you get less water. More of the water dissociates into ions. And what that means is you actually change the pH of water if you raise its temperature above 20 or change its temperature from 25 degrees Celsius to something else. You can actually lower the pH of water if you raise the temperature because you get more hydrogen ions. That's why the definition of pH equaling 7 being neutral is a completely arbitrarily drawn line. Neutrality is not some sort of universal natural constant. It is simply yet one more thing human beings have picked from nature and decided, hey, this is what we'll make important. The auto-dissociation of water at what we consider room temperature, this particular compound that's important to us at a temperature that is comfortable for us. It's a completely anthropomorphic designation to call pH 7 neutral. But nevertheless, that's the convention we're going to use. So that's the convention you're going to use. So it may be made up, but we're still going to have to learn it, just like money. It may be made up, but it's going to be important to us. So the equilibrium constant for the dissociation of water is 10 to the negative 14. By the way, you don't need the 1, right? 1 times anything is that thing. So it's really just 10 to the negative 14. You can drop the 1, and sometimes you'll see me do that. Don't get freaked out. 1 times 10 to the negative 14 is 10 to the negative 14. One thing we know for sure is that the hydrogen ion concentration, the hydroxide ion concentration are always going to be equal in pure water. How do we know that? Because water can't produce more of one without producing the other, right? Every time water dissociates, it breaks up. Every time water breaks up, It must produce exactly one hydrogen and exactly one hydroxide. These must be equal. There's no way water can somehow produce more hydroxides without producing more hydrogen ions as well, right? That can't be, that's impossible. That's like saying, taking a pair of shoes and suddenly saying you have two right shoes and one left shoes. How can that possibly be when your pair of shoes only contained one left and one right? Impossible. Well, just like water only contains one hydrogen ion and one hydroxide ion, it can't possibly make an unequal number of those. So if we know that hydrogen ion concentration in pure water, and only in pure water, if we know that these are equal, then we can actually figure out the value, the specific value of hydrogen ion molarity and hydroxide ion molarity. How do we do that? Well, if we know the dissociation constant is 10 to the negative 14, and we know that the product of two things that have equal value equals 10 to the negative 14, that means if X equals hydrogen ion, then X must also equal hydroxide ion, right? If these two are the same, then X must equal both. So we take X times X equals 10 to the negative 14. When we solve this, X squared equals 10 to the minus 14, we get X equals the square root of 10 to the negative 14. Now, please don't be one of those people that thinks that's a negative number, right? 10 to the negative 14 is a positive number. It just has a negative exponent. It just means it's a very small number. If you take the square root of 10 to the negative 14, what do you get? Well, what times itself gets you 10 to the negative 14? Well, 10 to the negative 7 times 10 to the negative 7 equals negative 7 plus negative 7 equals 10 to the minus 14. Therefore, 10 to the negative 7 is the square root of 10 to the negative 14. Of course, you can just use your calculator as well. Okay, so that's 10 to the negative 7. That means the hydrogen ion and the hydroxide ion concentrations in pure water at 25 degrees Celsius, pure deionized distilled water, these are the concentrations of hydrogen ion and hydroxide ion. We are getting toward the derivation of the pH scale. The pH scale is a logarithmic scale for measuring the acidity of a solution or the basicity of a solution. So the pH of pure water, therefore, is going to be this. We're going to take these concentrations because the numbers can vary so wildly and widely from one another, because they can go across orders and orders of magnitude from 10 to the minus 10 all the way up to 10 to the positive 10 or more. Because there's such a huge variance in the different concentrations or molarities of hydrogen and hydroxide ion concentrations across the many different types of solutions, a logarithmic scale, meaning a scale that only counts in powers of 10 rather than counting actual numbers, was developed to measure pH. And the way you use a logarithmic scale is you use the logarithmic function on your calculator, usually designated with the three letters log, logarithm. And so the pH is calculated by taking the negative log of whatever your concentrations are. So in this case, if I want to take the concentration, the molar concentration of hydrogen ion, that's 1 times 10 to the negative 7, or 10 to the negative 7, right? So I take the negative log of 10 to the minus 7. Logs count powers of 10. Therefore, the log of 10 to the negative 7 is negative 7 powers of 10, or negative 7. The minus here is simply because it's sort of an admission that, hey, most of the time when you do this, you're going to end up with negative numbers. We don't like negative numbers. Therefore, let's put a negative sign in front of our log and get rid of all these negative numbers. That's all it's there for. It has no other mathematical meaning than that. It's just the convenience of dealing with positive numbers rather than having to think about negative numbers. That's not to say you'll never end up with a negative value of pH or POH. You can, definitely can. There are lots of solutions that have negative pHs. It just means they're more acidic than normal, or than the usual range. So when you take the negative log of 10 to the minus 7, you get a negative of a negative 7, which is positive 7. This has been voted in And that's how science works. You vote. No, I'm kidding. Well, somehow some people, some group of scientists somewhere decided that this is the definition of neutrality. This is neutral pH. This was set as a definition. It's completely arbitrary. I'm telling you, it's just something chosen by human beings for convenience sake. But that is the definition of neutral. When the pH of a solution is 7, we consider that solution to be neutral. What that means is that we're making the assumption that we are at that we're at 25 degrees Celsius, and therefore the hydrogen ion concentration and the hydroxide concentration are equal. Or put it another way, the number of moles of hydrogen ion in the solution is exactly equal to the number of moles of hydroxide ion. Technically, that's the true definition of neutrality. Regardless of what temperature you're at, it's when hydroxide ion and hydrogen ion have equal number of moles in the same solution. That is neutrality. And that can happen at any pH, but for the most part, you're going to be measuring that pH at 7. That's why it was chosen. It's whenever hydroxide ion and hydrogen ion are equal. Their molarities are equal, or simply the sheer number of moles of each in the same solution, or in the same liquid, beaker of water, aqueous solution, in the same solution are equal to each other. Whenever that happens, that's considered neutrality, and that's considered completely neutralized. Acids and bases are neutralized. Remember neutralization reactions, the reaction of an acid with a base in a double displacement reaction. Okay, so the pH scale. The pH scale measures primarily the concentration of hydrogen ions in a solution. The greater the proton concentration, the more acidic a solution is. The more hydrogen ions you have, the more acidic. Hydrogen ion goes up, acidity goes up. Hydrogen ion concentration goes down, acidity goes down, or basicity goes up. Basicity, basic, is the opposite of acidic. The pH scale is a logarithmic scale. It counts power in powers of 10, rather than counting individual numbers, because the numbers are vast, the range of numbers and the range of solution concentrations is just ginormous. It's just like the Richter scale used to measure the strength of earthquakes. For example, an earthquake of magnitude 7 is 100 times stronger than an earthquake with magnitude 5. If the Richter scale were simply a regular scale, not a logarithmic scale, then 7 would represent only a 40% increase in strength. If the Richter scale were not truly a logarithmic scale, or were just a regular old scale, then a Richter scale value of 7 versus 5 would represent a 40% increase, or 1.4 times stronger. A 7 earthquake would be 1.4 times stronger than a 5 earthquake. But that is not the case. Because the Richter scale measures powers of 10, what it's really saying in shorthand form, and that's really the main advantage, in shorthand form, what it's saying is that a 7.0 earthquake is 10 raised to the 7th power versus 10 raised to the 5th power, which is 10 to the 7 minus 5. So that means that we have 10 squared, or 100 times stronger. A 7.0 earthquake is 10 squared, 10 to the 7 minus 5 times stronger than a 5.0 earthquake, because it's counting powers of 10. 10 to the 7th means 7 tens. 10 to the 5th means 5 tens, 5 powers of 10 multiplied to each other. This is also referred to as orders of magnitude. A 7.0 earthquake is 7 orders of magnitude, or in other words, 2 orders of magnitude greater than a 5.0 earthquake. That's what that 2 would represent here, 2 orders of magnitude greater than, or a 2-order magnitude difference between a 7.0 earthquake and a 5.0 earthquake. An 8.0 earthquake would be 3 orders of magnitude stronger, or 1,000 times stronger than a 5.0 earthquake, etc. So just like the Richter scale to measure earthquakes, the pH scale is a logarithmic scale. It is counting in orders of magnitude because there are such big differences in solution concentrations. It just wouldn't make any sense to you take a scale that measures 1 by 1, that counts 1 by 1. So most of the values in the pH scale go from 0 to 14, but I don't want you to take that and think that's the limit. Not at all. There are negative pH values and there are pH values above 14, even 15, even up to 30. The super strong acids have pHs in the range of 30 to 50. 30 to 50, 50. So, and you can easily, there are plenty of solutions in the stock room and in the lab at school that have pHs like are -1, -2, -3 even. It's not that hard to come by. Sorry, did I say pH 30 to 50? pH -30 to -50. Sorry, -30 pH, -50. These are super strong acids. A pH greater than 7 is basic. A big pH, okay, so just be careful. Even though pH measures acidity, a high pH value means basic. A low pH value means acidic. The lower these numbers get, the more acidic the solution is. A negative pH is a very acidic solution. A high pH above 7, above 14 or 15 is a very basic solution. Here's some examples of basic versus acidic stuff. Soaps and detergents are generally basic. They have a bitter taste if you've ever eaten soap. I'm saying bad words or something, I don't know. Baking soda also tends to be basic. Anything that tastes bitter. Now, baking soda, I think, tastes salty more than bitter, but that's only because it happens to be sodium in there. But for the most part, most bases taste bitter. Caffeine, for example, is a base and it tastes bitter. Dark chocolate, theobromine, is a compound that looks very much like caffeine. It's a little bit different. It's found in dark chocolate, especially, actually just chocolate. Most of the chocolate is dark chocolate until you add a bunch of other things to it, like fat or cocoa butter, cocoa fat to it. And so it's very bitter. If you ever had pure dark chocolate, it's very bitter because you haven't lightened up those basic compounds. Blood pH is slightly basic at around 7.35, just over the 7.0. Just over the 7.0 limit. Blood, human blood anyway, is slightly basic, and it's maintained there by a buffer system based on bicarbonate ion, which we'll take a look at later. A pH lower than 7 is acidic, so low pHs are acidic, so be careful. Even though this scale is designed to measure acidity, it's the low end of the scale that says something is acidic. Examples of acids. Orange juice, ascorbic acid and citric acid are some of the main flavorings that are for citric or citrus juices. That's why they're sour. Stomach acid, hydrochloric acid. Your stomach has a pH of around 2. Orange juice has a pH of around 3. So does soda, Coca-Cola, etc. Vinegar has a pH of around 5. That's because vinegar is actually only about 10% solution of vinegar. The rest of the other 90% is water. Anything that tastes sour is generally acidic. pH is determined by concentration, not necessarily by the strength of the acid. Of course, the strength of the acid can help bolster concentration, but it is not necessarily all up to just the identity. You can have a solution of a strong acid with a higher pH, thus a less acidic pH than a weak acid, depending on their relative concentrations. Let's take a look at some examples. First, make sure you know how to use your calculator. Make sure you know how to use the log function and the anti-log or inverse log function. On the TI-30X, usually that involves hitting the second button. Let's see if I can even find the relative. Oh yeah, right underneath. On the TI-30X 2S, you have your second button and you have your log button. If you just want to use the log function, just press that button. If you want to use the inverse log, press second, and then, oh, great, first, second, that's nice. First press second, then press the log button. For the inverse log, or the 10 to the x function. So remember, to use alternate functions on your calculator, your scientific calculator, you often have to press an alpha button or a shift button or a second button or some kind of special button that uses the alternative functions that are usually written right above the button, not on the button, but above the button on your calculator. Those are your alternate functions. And pressing shift or second activates those functions instead. So make sure you know how to use both. Just to calculate simple pH, though, we just need the log button. We don't really need the second button. The second button will be used for inverse logs later on. But for this example, to calculate a simple pH, we just use the log function. Okay. P, by the way, P generally stands for just take the negative log of whatever happens to be in front of P. If it's pH, take the negative log of hydrogen ion molarity. If it's POH, take the negative log of hydroxide ion. If it were, for example, pKa, you would take the negative log of whatever the Ka value is, or pKw. pKw equals take the negative log of Kw, which would be the negative log of 10 to the minus 14, which would be what? Well, logs count powers of 10, right? So that would be negative 14, that would be positive 14. Right? So the pKw, the auto dissociation constant of water, the P of that would be the negative log of that, which would be 14. It would just tell you what the absolute value of the, or I should say the reverse value of the exponent is. Okay, let's take a pH of 7.81 times 10 to the minus 3 molar HBr solution. So remember, hydrobromic acid is a strong acid. So we know it's going to dissociate completely. So we know that whatever its concentration is, the concentration of the concentration of hydrogen ions is exactly the same because it fully dissociates. HBr fully dissociates into hydrogen ion and bromide ion, which means if we have 7.81 times 10 to the minus 3 here, we also have that same concentration for both of our ions, but we don't care about bromide. We only care about hydrogen ion because these are acids and bases we're talking about. We only care about hydrogen ions, and when it comes up, hydroxide ions. I wrote EE here just because that's what your calculator will make it look like, and then you'll type in -3. So make sure you know how to use your scientific calculator, especially when you're taking the negative log of something. Be very careful there. Depending on your calculator, it's easy if you don't use the proper scientific notation function on your calculator can very well misunderstand what you're trying to calculate. It might, if you just type in 7.81 times 10, raised to the -3 or something like that. If you type that in, your calculator will probably think you want to take the log of 7.81 and then multiply the result by 10 to the -3. And that is not the same number. That is not at all the same number, totally different number. So be very careful about the way you handle this input. If you find yourself consistently getting different numbers from mine on these examples, it's because you're not using your calculator correctly. Also, be sure you don't type in 10 EE to the -3 or something like that. Don't type in 10. If you're using the scientific notation function, you do not need to type the number 10. The calculator understands. If you know how to use the calculator and you're using its proper scientific notation function, it already understands that there's a 10 that needs to be raised to the power you're inputting. You only input the power, not the 10. Otherwise, you're effectively multiplying your number by 10 for no reason at all. So be very, very careful. Make sure you go through these examples with me. If you have any doubts, make sure you're coming up with exactly the same numbers. Also, these numbers are going to get, this topic of calculators will never go away, but also be aware that these numbers are going to be very big and very small sometimes, which means if you don't have your calculator set to give you information in scientific notation, oftentimes you're going to get a screen full of zeros. That's not because your answer is 0. It's because your calculator simply doesn't have the screen space to show you the number in typical flow or decimal notation. So my advice to you is not to think that that's the answer, but instead to change the output of your calculator. Again, if you're using the TI-30X, press the second button, and then press the button right next to it, the DRG button, and then pick psi, hit enter, and then hit equals. Well, select psi using the arrow keys, and then hit the equal button. Sometimes it'll ask you to pick the number of digits that you want to represent. Just pick the maximum number, 9 digits. I'm just trying to see if my calculator asks me that. Well, my calculator didn't ask, but sometimes calculators ask you that. Sometimes it'll say like 0 to 9 and it'll ask you a question. Just pick 9. Just type in 9. Give yourself the maximum number of digits. Don't try to round, otherwise it'll round up to like whatever number you pick, or it'll give you 1-digit answers if you don't pick anything. So be careful about that. There's a lot of complications with scientific calculators if you don't know how to use them. See the instruction manual as well. You can download instruction manuals for any calculator off the internet. You don't even need the one that came with the calculator. Okay, so this is what I get. I take the negative log of this and I get 2.11. Make sure, I'm going to double check myself just in case right now, because I really don't, this is not the time I want to make any kind of mistakes with you, especially if I really want you to check your numbers along with my numbers. So I'm going to type it again, 7.81 second EE. So I type in the second button, and I type in the EE. It says EE above the button, not on the button directly. The button itself says x to the -1, but it's the EE is written right above it. It's not on the button. It's written in some other color on above the button on the plastic back of the thing. Anyway, -3, and use the plus minus button. Don't use the subtraction button. Yeah, I get 2.107. 2.107348, whatever, etc. So that's what I got. So make sure that you are getting the same answer. Anyway, you can generally tell where your answer should be because remember, logs count powers of 10. If I'm counting log of 10 to the -3 or something to the, something to the minus, yeah, times 10 to the -3, that should put me somewhere around 3, but of course I've got 7 there, so that's going to put me somewhere between 2 and 4, and indeed my answer is 2 point something. So practice looking at the exponent and just realizing about approximately what order of magnitude should I be at when I'm done calculating this. You should be within a digit or two of the negative value of your exponent. So that should tell you whether you've done something really off or not. Okay, so the pH of this strong hydrobromic acid solution was 2.11. That's less than 7, so it checks out. This is an acidic pH, so that makes sense. That's another thing. If you get a pH value that's over 7 for an acidic solution, something has definitely gone wrong. Let's do another one. How about the pH of acetic acid? Remember, acetic acid is a carboxylic acid. It's a carbon-containing acid. It's going to be a weak acid. How else do you know it's a weak acid? Well, here I'm going to tell you right off, oh, only 5% of my acetic acid molecules dissociate. What does that mean? That means my HC2H3O2, only 5% is going to become H+ and acetate ion. That means 95% remains intact hydrogen acetate molecule, and only 5%, well, what do I have? I have 3.6 molar, right? Okay, so what does that mean? If I have 3.6 molar, what's 5%? Well, convert your percent into a decimal, and then multiply that by 3.6. So I get, I know I already did, but I'm going to do my numbers again here. I get 0.18. So that gives me 0.18 molar H+, because only 5% of my molecules actually dissociated to give me H+. So that's 0.18. By the way, that also gives me 0.18 molar acetate ions, but I don't care about acetate ions. Remember that. You don't care about anything other than hydrogen and hydroxide. This is a very narrowly focused section of chemistry where our focus is only on the stuff that affects pH, hydrogen ions and hydroxide ions. So that's our concentration. That is our H plus. And so we plug H plus into our formula for pH. pH equals negative log of H plus, negative log of the 0.18. Now notice, we do not type in the 3.6. Why? Because that wasn't the concentration of H plus. Our concentration of H plus was dependent on this factor, which I had to give you because there's no other way you could have known that. Seriously, there's no way. You cannot guess. You can't even look it up because I'm kind of making these numbers up. They're close to the truth, but they're not exactly the truth. Like I said, for convenience, I have to pick numbers that are within reason for us to calculate. All right, so log of 0.18. 0.18 is like 10 to the minus 1, right? Anything less than just under 1 is 10 to the minus 1. So it's approximately, you should expect a value that is approximately 1. We get a value that is 0.74, which is approximately 1. If you were to round it up, it would be to one digit, it would be 1. And that's what we get, and that's what we should expect. So just practice guesstimating what your numbers should be, at least within a ballpark, within an order of magnitude. And so that should be your answer. Yeah, I rounded to 3 digits. You can have more digits, but as long as your digits round, as long as your number rounds to this, you're good. So look at this. Let's compare. So the acetic acid, the weak acid solution, not the weak acid itself. You can't measure the pH of a compound. You can only measure the pH of a solution. And of course, solutions have variable concentrations. The weak acid solution was more acidic. Weak acid solution pH was less than the strong acid solution pH. So the weak acid solution was more acidic. Remember, a lower pH means more acidic. It didn't lose, it won, right? It won the acid contest because it had a lower pH. It's like golf. The lower your score, the more you win. I don't play golf, but that's my understanding anyway. Okay, so weak acid solution was more acidic. It had a lower, wait, what? Yeah, had a lower pH, yeah. 0.745, oh, here it is. I was looking at the wrong number, sorry. 0.745 is less than 2.11. Lower pH, more acidic, because it had a greater concentration. The fact that it's a weak acid doesn't mean you can't put enough of that acid into solution to get the hydrogen ion higher, concentration higher. Also, you can have a very, very dilute strong acid solution, so dilute that the acidity, even all those dissociated protons just still aren't enough to reduce the pH to the same level. So be careful about that. Don't assume strong always means more acidic. It doesn't have to. Usually it does. And by the way, if these were the same concentration, yeah, the HBr would blow it out of the water. It would be extremely acidic. If these happen to be the same constant, regardless of which concentration you use, if both of these had equal concentrations, if the molarities had been the same, if this molarity was X molarity and this molarity was also X molarity, yeah, this would be the lower pH for sure, no doubt. When you all else being equal, same concentration, the strong acid will always have a lower pH than a weak acid. All else being equal, meaning having the same concentration, the same molarity. But if the molarities are different, then you're going to have to do some math to really work it out and figure out which one is stronger, which one is weaker. So be careful. Okay, let's do some more examples. Do strong acids always have lower pH? Well, this is kind of the same idea, isn't it? This is just one more of the same. The answer is no. No, they don't. No, they don't. So let's go through this. This is kind of just a rehash of the one we just did. By the way, do you notice I'm using a different value for the Ka, the dissociation constant for hydrofluoric acid. This one, I made this one I think I made this one a lot higher. Was the other one 0.01% or just 1%? Anyway, I might be using a slightly different value for HF. Don't worry, it's close enough. For our purposes, it doesn't matter what the true value is. Okay, what is the pH of a 3.73 times 10 to the minus 4 molar per chloric acid solution? Remember, this is a strong acid. This is on your strong acids list. That's another way you can tell. Just look at your strong acids list. But memorize those lists. Don't rely on having to look at lists constantly. You're not doing yourself any favors by doing that. So number one, let's calculate that. pH is equal to the negative log of the H plus concentration. This is a monoprotic strong acid. Therefore, its hydrogen ion concentration is equal to its overall concentration, right? These concentrations are the same because it's monoprotic. There's only one hydrogen ion and it's strong, so it's going to completely dissociate. Therefore, if that's the case, we can put the 3.73 times 10 to the negative 4 into our pH formula and just calculate it directly. And so what do we get? Well, okay. Well, I get 3.43. I'm going to round to 3 digits. 3.42829. I'm just going to round to 3.43 as my pH value. Does that make sense? Well, I have a negative 4 here, but I have some low value here, which means it's a little bit lower than negative 4. It's like between negative 4 and negative, sorry, a little higher than negative 4. So it's like between negative 4 and negative 3. I ended up with a 3. Remember, you take that sign, you cancel the sign out, the negative out. So it's around 3, which is within an order of magnitude of my exponent on the 10. Okay, anyway, so that's my answer to number 1. Answer to number 2, for the 1.42, notice how much bigger I made the solution concentration here. This was 10 to the minus 4. This is like 5 orders of magnitude almost greater. So of course I made this, I stacked the deck in the favor of HF just to make my point that weak acids don't necessarily mean higher pH or less acidic. So I'm going to do the same thing. Again, this is a monoprotic acid, but this is a monoprotic weak acid. Look for some data. You need more info. You can't just use you can't just use the concentration as a given. So I looked for some data. Oh, what do you know? 1%. So 1% of the 1.42 molar is going to equal 0.0142 molar, right? That's 0.01 multiplied by 142. That gives me, well, let me just double check my math because we know that I am easily capable of making errors. 0.0142, yeah, that's what I got, 0.0142, right? That's my actual concentration of acid, of hydrogen ion. So be careful, take that 1% into consideration. It's a weak acid, therefore there's got to be some kind of factor. You can't just assume you can't assume this. Unlike strong acids, these are not going to be equal. The concentration of HF and the concentration of H plus are not going to be the same. You have to use some information that's given to you, and it will be given to you. That information has to be given to you because you have no other way of figuring it out. There's no logical way to come to it. So negative log of 0.0142. pH, by the way, has no unit. So it doesn't matter if you put molarity in there or not. Once you do the pH calculation, there is no unit for it. So negative log of that gets me 1.85. Again, I'm rounding. It's 1.8477116, blah, blah, blah. I'm just putting 1.85. I'm going to round. Don't worry about sig figs and rounding with logs. There are rules for it, but they don't really interest us. We're not going to deal with those with logarithm sig fig rules. Okay, so it turns out that 1.85, of course, is a lower pH than 3.43. Therefore, we can conclude that in this case, our weak acid solution, not the weak acid itself, this particular weak acid solution with this particular concentration was more acidic than the strong acid. But that's only because I chose my concentration values to make this point. It doesn't always have to be that way. My point in general is this: don't judge a solution by the solute, by whether it's a strong or weak acid or base. Don't judge it by that. You have to measure the concentrations and then do the math. You can't make a priori assumptions, meaning you can't make assumptions without actually investigating. Okay, here's another one. Which of the following solutions has a higher pH? Now, you might find it strange because I'm asking about pH, and yet what kind of solutions are these? Are these acidic solutions or basic solutions? These are both basic solutions. Now, you can actually calculate this right off. You can. In fact, we're going to take a look at some formulas to help you do that. But for now, I haven't introduced those formulas, and I'm just going to go ahead and assume A, that you're not going to use, you don't know them, or B, that we're not going to try to use them. Instead, we're going to base this on principle. So what is the principle here? Remember, the more, so it says higher pH, right? What it's really asking is which one is more, this equals more basic, or another way of saying it is higher concentration or higher molarity. We only deal with molarity, by the way. I don't know if you've noticed that, but we're only dealing with molarity. Out of all those other percentages, really in this section, we're basically just going to stick to molarity. Higher concentration of hydroxide ion, the base ion, the ion that represents bases. Okay, so higher pH means more basic, which means a higher concentration of hydroxide ions. So we want to see which of these has the higher concentration of hydroxide. Well, first we have to ask ourselves a question. Strong versus weak bases. Are these both, is one of them strong and one of them weak? That's the first thing we have to get out of the way. No, both are strong. By the way, if both had been weak, that would actually be very confusing. And if one were weak and one were strong, depending on which one was strong and which one was weak and the relative concentrations, we'd have to, it could either just be a slam dunk answer or it could be confusing as well. In this case, they're both strong, so no issue. We're comparing apples and apples. Apples to apple comparison, right? Or apple to apple comparison. iPod to iPod. Are those even a thing now? I don't even know. Whatever. I don't buy Apple products, so I don't know. No issue, apple to apple comparison. So that's good. So the only other thing we have to figure out then is the concentration or the moles of hydroxide ion per mole of base. Or in other words, I made that sound even more, I think that's unnecessarily complicated. All I really have to figure out is what's the concentration of hydroxide for each one of these solutions. We can actually, I have 2 more slides devoted to explaining this in excruciating detail, but we can figure this out right now. Let's do that. Let's not worry about I'll let you read through the next 2 slides on your own if you feel like it, but I think you're going to understand this quite readily. Okay, since we're comparing apples to apples, all we need to do is compare the relative hydroxide ion concentration. Well, let's look at the first one. I have 0.6 molar calcium hydroxide, but each calcium hydroxide has 2 hydroxide ions. So we take 0.6 molar here, moles of, I'll even, let me write it out like this, 0.6 moles per liter, that's the definition of molar, moles per liter of calcium hydroxide For every 1 mole of calcium hydroxide, I don't know if this makes things easier or harder for you. You let me know. 2 moles of hydroxide, right? 2 moles of hydroxide. The formula is telling us that there are 2 hydroxides for every 1 calcium hydroxide. If we have 1 calcium hydroxide, 1 formula unit, then we have 2 hydroxides. If we have 1 mole of calcium hydroxides, we have 2 moles of hydroxide. So that gives us 2 times 0.6, or 1.2 moles per liter, or 1.2 molar hydroxide ion. Not calcium hydroxide. We are looking specifically at hydroxide ion. Remember, all we care about when it comes to acids and bases are hydrogen ions and hydroxide ions. Everything else can go by the wayside. We don't care. How about potassium hydroxide? Well, potassium hydroxide is a 1-to-1 ratio. So what you see is what you get. It's 0.8 molar hydroxide ion, because mono basic, just like monoprotic and strong, monobasic, strong base means that your hydroxide ion concentration equals your potassium hydroxide ion concentration, or potassium hydroxide concentration. They're one and the same. So the 0.8 molar applies to the hydroxide as well. So which one do we have more of? Well, 1.2 clearly is bigger than 0.8. So 1.2 is greater than 0.8. Therefore, this is our winner. The calcium hydroxide, which ostensibly has the lower concentration, actually has the higher concentration of the most important ion for bases, for base consideration or acid consideration. It has double the number of hydroxide ions. So so which of the following solutions has a higher pH? The answer, calcium hydroxide has the higher pH. 1.2 molar hydroxide ion versus 0.8 molar for the other one. That is our answer. Remember, higher pH indicates higher hydroxide ion concentration, lower hydrogen ion concentration. Higher pH means more basic means more hydroxide ions. And all of this just goes through that in lots of detail, but basically I say the same thing. I relate all of these, and if you want to read through this like one step at a time, go ahead, but that's what we just did. We just did exactly what these 2 slides are going into detail about. The thing to remember now, one thing that is not a kind of a repeat here is this part right here. The thing to remember is that the higher the hydroxide ion concentration, the lower the H+ concentration, and vice versa. This is a very important part. It's probably the reason I didn't delete this slide. But I say this elsewhere as well. The ions are inversely proportional. This is, and again, if you understood all that stuff about inverse proportionality versus direct proportionality and all that stuff from the gas laws about Boyle's law, or molarity times volume equals equaling number of moles from the dilution formula, or later on, the titration formula, you'll understand this as well. Remember, the hydrogen molarity multiplied by the hydroxide molarity equals literally a constant. And we actually know the constant in this case, it's 10 to the negative 14, no units. 10 to the negative 14. When the product of 2 variables equals a constant, they are inversely proportional, meaning the only way to maintain a constant, if you change one of the variables, for example, is to change the other one in the opposite direction. So for example, if somehow I increase the concentration of hydrogen ion, the only way that the 10 to the minus 14, which equals the product of hydrogen ion and hydroxide ion, the only way that this number doesn't change is if the hydroxide ion goes down to compensate, and vice versa. If I were to raise the hydroxide ion concentration, the only way to keep this constant is to reduce the hydrogen ion concentration. It's a seesaw. Whenever one side goes up, the other side must go down, and vice versa. There's simply no option to this. So when the higher the hydroxide ion concentration, the lower the hydrogen ion concentration in any solution, anywhere, anytime, regardless of temperature, regardless of anything. And the lower the hydrogen ion concentration, the higher the hydroxide ion concentration. They move in opposite directions. That's why I'm able to say that the lower the, sorry, what was the question again? Oh, here, right here. Higher pH. The higher the pH, the more basic. The more basic, the more hydroxide ions. The more hydroxide ions, the fewer the hydrogen ions. They can't both increase because that would change the value that they multiply out to. It would change 10 to the minus 14, and 10 to the minus 14 is a constant. It may be arbitrarily chosen, but it is a natural phenomenon. So it just happens to be one that was picked out of many other natural phenomena. Okay, these are the different formulas that express the exact same thing I just said. All of these formulas, it looks like a lot of formulas, but guess what? Every one of these formulas is just a different manifestation of this fact. That's it. These are 6 formulas, 4 plus the 2 on the bottom, 2A and 3A. 6 formulas to say the same exact thing, just in slightly different ways, slightly mathematically different ways. So the first one is what we just talked about, that hydrogen ion and hydroxide ion, the product of those equals the dissociation constant of water, 10 to the minus 14. So they are inversely proportional. If one goes up, the other one goes down. This, by the way, if you were to take the logarithm of both sides of this formula, if I were to take the log of hydrogen times, or the negative log, let's say the negative log of both sides. In other words, if I were to take the log of both sides and then stick a negative sign on the result, if I were to do that, I would actually get the definitions of pH and another thing called POH. That's because this has to do with a property of logarithm, the logarithm function, which is that the log of the product of the sum of the logs. I know it sounds kind of funny, but it sounds like I don't know, sounds like some sort of limerick. The product of the log of the product of the sum of the logs, but that's what it is. In other words, the log of something times something equals the log of the first thing added to the log of the second thing. So if I take the log of hydrogen times hydroxide, I can break that up into the log of hydrogen ion plus the log of hydroxide ion, and that's equal to, well, that's the very definition. The negative log of hydrogen ion is pH, and the negative log of hydroxide ion is POH. POH is just the measure for basic solutions. POH is in very much, and I wrote this somewhere else here. Yeah, here it is. The POH scale is the exact reverse of the pH scale. In other words, the higher the POH, the more acidic. The lower the POH, a low POH means more basic. Just like a low pH means more acidic, a low POH, which measures basicity, a low POH means more acidic, means more basic, more basic. pH of 7 is exactly neutral, just like pH. So the POH scale is the exact flip side, or the upside down of pH. Anyway, one thing that this tells us, this pH plus POH thing, means if we take the log of 10 to the negative log of 10 to the minus 14, we get 14. That gives rise to equation number 4 over here. The sum of the pH plus the POH equals 14. This is exactly the same thing as this, only this is expressed in logs, whereas the equation number 1 is expressed in regular old decimal units. Number 4 is just number 1 expressed in logs. The pH, remember, is a logarithmic scale. So is POH. Log plus log equals log of 10 to the minus 14, which is 14. But you want to know the pH of a solution. Just subtract your POH from 14 and you've got your pH, and it works every time. That's the number. That pH and POH differ by 14 units. We're going to do some examples of this. So, pH you've already seen, that's just the negative log of the hydrogen ion concentration. POH is just the negative log of the hydroxide ion concentration. Everything that exists for acids and hydrogen ion also exists for hydroxide ion and bases. It's the same thing. It's just another version, but devoted to the other most important ion in this section, which is hydroxide. Hydrogen ions are important, but so are hydroxide ions. Together, they make up the seesaw of a solution's pH, or basicity or acidity. Now, we're more familiar with pH, the pH scale from everyday life. You've probably heard of pH, but you may or may not have ever heard of POH. But it's exactly the same thing, just in reverse, measuring the basicity instead of measuring the acidity, although they both measure both, right? If the pH is above 7, that's a basic solution. It's telling you how basic it is. The POH scale is mainly used to directly measure the acidity or basicity of hydroxide ion-based solutions. Down below 2A and 3 POH, you're given pH or POH, and you need to work your way backwards to the actual concentration of hydrogen ion or hydroxide ion. So for example, if I tell you, hey, this solution has a pH of 6.7, but you want to know what the concentration of hydrogen ions is in it, then you'll say, okay, well, I'll take that 6.7, I'll take the inverse log of the negative pH, so I'll take the inverse log of negative 6.7, and that'll give me the concentration of hydrogen ions. The way these are not different formulas. These are the same formulas as 2 and 3. All we did was solve for a different variable. How did we get them? Well, if pH, I'll do one example for pH equals the negative log of H plus, right? What if instead of solving for pH, what if I want to solve for H plus? What's H plus? Well, what I can do is I can say, okay, let me just go ahead here and divide both sides by -1 to get that negative out of there. So I get negative pH equals log of H plus. All right, well, put parentheses around this. How do I solve for log of something? Well, there's an inverse function. For example, for a sine function, there's an inverse sine function. For cosine, there's an inverse cosine. Well, no different here. For a log function, there is an inverse log function. Remember, logs count powers of 10. So what you can do is you can take the inverse log of both sides. Whatever you do to one side, you must do to the other side. So take the inverse log of both sides. What does that equal? Well, the inverse of a function makes that function disappear. So we end up with H plus on the right side, and we end up with the inverse log of negative pH on the left side. What's the inverse log? Another way of writing or calculating inverse log, you can either use the second function and the log button, press sequentially, press this and then press this, 1, 2, second and then log. If you have a TI-30X2S calculator, if you have a Casio, it's a different button somewhere. Let me know if you have any trouble with that. Or the other thing you can do is you can just say inverse log of something. Taking the inverse log of something is the same thing as taking that something and turning it into the exponent on 10. So 10 raised to the negative pH. Whatever pH is, just put a negative sign in front of that number and make it an exponent. In other words, you would take 10, use that power button, and then the negative button, and then your pH. Just type in your pH, whatever it happens to be. So we're going to do some examples right now with that. But that's the idea. So you're just solving for a different variable. 2 and 3 and 2A and 3A are exactly the same formulas. They're just rearranged in order to allow you to solve for concentration of these ions instead of solving for pH and POH respectively. So let's jump into some examples. Okay, POH of an acid. POH of an acid. We're going to go through a bunch of examples here. So this one in particular isn't the one I was talking about. But what would be the POH of a 0.22 molar acid, nitric acid solution? Now, of course, it's important for you to know the difference between strong and weak, and also the difference, and you should know the formulas of acids to know whether it's monoprotic or or polyprotic. So nitric acid, I'll just let you know, is a monoprotic strong acid. It has one hydrogen and it is strong, which means its concentration is equal to the concentration of hydrogen ions you're going to get from this. In order for that to be the case, it has to be monoprotic and it has to be strong in order for that to be true, for the concentration of the compound overall to be the same as the concentration of the protons. Okay, so what's the pH? Well, let's do this. First, step one, let's figure out the pH. So pH is going to equal the negative log of the hydrogen ion concentration, which is going to be 0.222. I don't bother with the molarity unit because the pH doesn't have a unit, so it doesn't matter if I put it on. Okay, so if I take the negative log of that, I get 0.654. 0.654. And again, no units. That's pretty acidic, right? Let's just do a little logic check here. This is nitric acid. Do we have an acidic pH? Yeah, we do. It's below 1. It's not only below 7, it's below 1. It's really acidic. Nitric acid is a strong acid. 0.2 isn't that great of a concentration, but I guess it's strong enough to make this thing a decimal number. If that's our pH, what's our POH? Well, going back, we know that the pH plus POH equals 14 for every single situation. That's number 4. Here it is. I don't know why I put it so far. That's number 4. There's no particular order to this, by the way. If you want to rewrite this list in a different way, go ahead. I put it in order of importance, actually. pH plus POH equals 14, right? The rest of these are just rearrangements of that same formula. Okay, well, if the sum of them equals 14, that means POH plus 0.654 equals 14. So POH, therefore, must equal what? Well, just subtract 0.654 from both sides. And so we get 13.346. I am definitely going to do this subtraction on my calculator there because I do not trust myself. 13.346, yes, indeed, thank goodness. Okay, and that's our answer. So we calculated the pH, then we converted pH to POH by using this very easy formula. We know that the sum of pH and POH is always going to be the same number, 14. Let's do some more examples. Molarity from the given pH. Now this is the one that's going to use the inverse log function. We want molarity. We're given pH. We're given a number in logarithmic terms. We want to de-logarithmify. That's not a real word. We want to de-logarithmify the number. That's all we're doing. So number 1, what is the proton concentration in a solution with a pH of 5.15? So if pH equals 5.15, and we know that pH is the negative log of H plus molarity or concentration, let's just solve for this. Solve for H plus. How do we do that? We take the inverse log of both sides. So I'm going to take, after we move the negative sign over, I'm going to take the inverse log of negative 5.15. Whoops, here's my eraser, 5.15. I move the negative over just to make my life easier, right? I want to take the negative inverse log of a complete number. I don't have to do any more math after that. If I take the inverse log of one side, I have to take the inverse log of the other side, but the inverse log of a log makes those two functions cancel out. So all I'm left with is H plus. The inverse function of a function is no function at all. That's how they cancel out. So that's going to be, on your calculator, you can actually just type it in like this, 10 to the negative pH. pH was 5.15. There's no point, you can't modify that pH. It's just a given. So 10 raised to the negative 5.15, or you can use the inverse log of negative 5.15. Either way you do this, you're going to get the same number. At least you should get the same number. In fact, do it both ways and see if you get it. If you get the same, I get 7.0879, whatever. I'm just going to round it. 7.08 times 10 to the negative 6 molar or micromolar. 7.08 micromolar but I'm just going to write 7.08 10 to the minus 6 molar. By the way, notice that this does have a unit, right? Once you remove the whole logarithm, and once you remove the pH stuff, you actually have units. It's molarity. Specifically, the unit is molarity. It always is. I'm going to do it the other way too. This way, I did it this way. I'm going to do the inverse log way. So I'm going to type in second log, so second log, that gives me inverse log. What pops up on my calculator, by the way, is this on the screen. Shows this. Then I'm going to type in my negative, which is in parentheses, by the way. I type in that button, 5.15. It helps if I actually type the number in correctly, 5.15. I get the same thing. And then I hit equals after typing in 5.15. And I get the same thing, 7.079 or 7.08 is what I'm going to round to, 10 to the minus 6. And of course, it's molar. By the way, this is micromolar. And you can actually write that if you want, micromolar. You can apply metric prefixes to whatever you want, if you really want to. I'm not going to do that to you, I don't think. Actually, you know what? I don't want to make any promises. Who knows? Okay, 2. So either way you do it, whether you actually straight up just type in the numbers 10 raised to the power of, negative 5.15, or if you actually use the inverse function on your calculator, either way, you'll get the same answer, or you should get the same answer. Number 2, what is the hydroxide ion of the same solution? Okay, now there are 2 ways you can do this. There are 2 ways. By the way, I'm going to make some space now, so I'm going to erase some of this. I'll keep the original answer. But actually, there are probably 2, maybe even 3 ways, now that I think about it, that you can actually calculate this. I'm going to do it at least 2 different ways. Method 1. Oops. Method number 1. I'm going to use this fact. It's a formula, but it's also a fact. That the product of the hydroxide and hydrogen ion in any solution is 10 to the minus 14. That means, since I already know what my hydrogen ion concentration is, I can just plug that number in, 7.08 times 10 to the negative 6 molar, multiplied by my hydroxide ion concentration, which is unknown, 10 to the negative 14 on the right side, solve for my hydroxide ion concentration by dividing both sides by 7.08 times 10 to the negative 6. Since I have the information, why not, right? 10 to the minus 14 minus 10 to the minus 6 is going to be 10 to the minus 8. So I should get something in that vicinity, within that order of magnitude, right? Within an order of magnitude of that, around 10 to the minus 8. I'm going to use my reciprocal button because I don't like to type that much. I'm going to use my functional keys here. I get 1.41 times 10 to the negative 9 molar hydroxide ion. Okay, now here's the thing. You can double check this several ways. You can take this number, multiply it by that number, see if you get 10 to the minus 14 within rounding, like something at least close to 1 times 10 to the minus 14. I'm going to do something else. I'm going to do a method 2. Let's try this a different way. Let's see if our answers agree. They'd better, otherwise I did something wrong. My other method is this. I know what my pH is. So if my pH equals 5.15, my pOH is going to equal 14 minus my pH, which is going to equal 14 minus 5.15. Remember, this is the same solution. So I can trust that it's the same pH, right? And that's going to equal 9.85. You know what? I don't trust myself one single bit anymore. So 14 minus 5.15. Aha, I knew it, 8.85. 8.85. So my pOH is 8.85. Okay, so I'm going to do the same thing now. Now I'm going to do the parallel to what I did earlier. This time, I know that my pOH equals the negative log of my concentration of hydroxide ions. And I know that my pOH is equal to 8.85. So I'm just going to solve. Hydroxide ion equals 10 raised to the negative 8.85. In other words, the inverse log of the negative pOH will give me my hydroxide, my OH concentration. So let me do that. And I get 1.41. Within rounding, these numbers agree. 1.41 times 10 to the negative 9 molar hydroxide ion. So there's my answer again. They agree. Thank goodness, huh? Is there a third way I could have done this? There probably is, but I don't think I'm up to the task. I don't know. If there is, it's probably not really worth doing. It's just going to be trying to find another way to do it for no other reason. Yeah, I don't really see another way. Everything else is just going to be redundant. Or it's going to be even harder than it needs to be. Actually, that's really the thing. Yeah, I think these are the only two ways you can really realistically do it, unless you're like trying to go out of your way. It's like traveling east to go west. Nah, this is it. So they agree, which is good news. If you want to, though, just as a final double check, you can always do this. 1.41 times 10 to the minus 9 multiplied by 7.08 times 10 to the minus 6. Final check, just for fun. That's my twisted version of fun. What's yours? 7.08 times 10 to the minus 6. Yeah, I get 1.000. I don't even see a non-zero digit until like the 100,000th place. And I'm not really going to care too much about that. That's just rounding. Times 10 to the minus 14. Checks out. So there you go. Because the hydrogen ion, hydroxide ion concentrations or molarities of any solution, their product, when you multiply them together, should be 10 to the negative 14. Doesn't matter if it's an acid solution, a base solution, pure water, makes no difference. As long as you're at 25 degrees Celsius, it'll be 10 to the minus 14. And the assumption is you're always at 25 degrees Celsius. Okay, here's another problem. Now, this is everything. This is all the questions regarding calculations that we could possibly do in this section. This is not titration or anything or buffers, but as far as working with concentrations and pH scale and pOH scale, this is probably the maximum you're going to see. So let's take a look at this. This is definitely worth your time to rework after this, or pause the video and work this out yourself and see if you can get it. So we have a 0.0833 molar dibasic calcium hydroxide solution. Dibasic, meaning we have 2 hydroxides per formula unit, dibasic. So let's start with the easiest question. What is its hydroxide ion concentration? Not so fast. Don't put 0.0833. It is not, is it? The hydroxide ion concentration is going to be 2 times 0.083. Every time one of these calcium hydroxide formula units goes into the water, what do you get? You get calcium and you get 2 hydroxide ions floating around. You do not simply get 1 hydroxide. So you get twice as many. Remember, the concentration on any reagent bottle isn't telling you what you specifically need to know. It's just telling you how many formula units are in there. It's up to you if you want to break up the formula unit and look at one piece of it It's up to you to do the math. So A is going to be 2 times 0.0833 molar, and that's going to be 0.1666 molar. And again, let me double check my work here because I don't trust myself, nor should I, nor should you. I mean me. 0.1666, yeah, molar. Hydroxide ion concentration. So we are not calculating the concentration of calcium hydroxide. We're calculating the concentration of the now dissociated and released into the water hydroxides. So be careful about that, because if you mess that one up, parts B, C, D, and E are all going to be lost. Well, actually, E, you might come to the same answers because it's comparing a tribasic to dibasic. The same relative answers. Okay, B, what is the POH? You don't have to do this in order, by the way. You can do this in whatever order you're comfortable with. I'm going to do B next, but you could jump to C if you want. In fact, I'm going to jump, after we do B, I'm going to jump straight to D, and then I'm going to do C, because that's just a lot easier. But let's do B first. What is the POH? So POH equals the negative log of hydroxide ion concentrations. This, conveniently, you've earned it. So just plug it in. And this is approximately 10 to the minus 1. So we get 0.778, approximately 1. 0.778 is our POH, no units, because pH and POH have no units. So that's our POH. That's the answer to B. Okay, next I'm going to jump to D. You don't have to do these problems in order. So I'm going to jump to D first. Why? Because it's so easy. pH plus POH equals 14. pH, therefore, equals 14 minus our POH. Well, we just figured that out, didn't we? Isn't it nice how these all work together? And that's going to be 13.222. Why am I bothering here? Minus 14, 13.222. Yeah, here's 222. 222. Again, no units. .13 plus 13.2 plus 0.77 or 78, that's 14. So obviously that works out. Now we'll jump to C. Now we'll do C. C is the one, again, you're going to have 2 choices for C. Let's do dark blue. You have 2 choices, and we're going to do both methods again. So C, method 1. We have lots of information to work with already now that we've done parts A, B, and D. We have lots of information to use, so we can start from any point we want. What is the H+ concentration, the hydrogen ion or the proton concentration? Well, we can either start from the hydroxide ion concentration and then just divide that into 10 to the minus 14, since we have that number. Well, it's not a bad place to start. Let's do that. H+, we know that the product of hydrogen ion and hydroxide ion equals 10 to the negative 14. So we already know the hydroxide ion. That was the very first thing we figured out. So we know that H+ times 0.1666 equals 10 to the negative 14. So we know divide both sides by 0.1666, H+ equals 10 to the negative 14 divided by 0.1666. Plus, this isn't so bad this time because we don't have to plug in like a giant scientific notation number, which is always nice if you don't have to do that. So I have 10 to the negative, actually don't type 10, then 10 to the negative 14. Just type 1 10 to the negative 14 using scientific notation, or, so another, or just if your calculator allows it, this is what I do. Second On my TI 30X2S, I do, this is literally how I started. The screen is blank. Second, and then I press the EE button, which is the X to the -1 button, right? X to the -1 button. Second EE minus, and then 14. I don't even bother with a number. Divided by 0.16666, I get 6 times 10 to the -14. Whatever you do, do not type 10 first. If you type 10, you're going to be multiplying your number by 10, and you don't want to do that. By the way, just to show you, this is exactly, or not exactly, but it's 6.00 times 10 to the -14. Wow, that's really close to 1 times 10 to the -14. This, really? Huh. This is a very, very basic, oh, well, you can see, yeah, very basic solution, 13, pH of 13, very basic, or POH of under 1. This is a very basic solution. Both of these agree, by the way. Both agree. This is a very basic solution. A very low pH and a very high, a very low POH and a very high pH, both are saying the same thing, very basic, high concentration of hydroxide ions. Okay, so 6 times 10 to the -14. This is a very, very low, practically zero concentration of hydrogen ions. Okay, so that's one way. And by the way, molarity, remember that, molarity. This time we're calculating concentration. We have a unit. Let's do method 2 now. Part C, method 2. Well, what other method? We have lots of information available to us. We use the hydroxide ion concentration. Now let's use, we're trying to figure out H+. Well, we have the pH, don't we? Yeah, we do. The pH is 13.22. So pH equals 13.222. So we know that the hydrogen ion concentration is simply going to be 10 raised to the negative pH, right? 10 raised to the power of negative 13.222. So 10 raised to negative 13.2222. I get 6 times 10 to the -14. Good. Actually, I got 5 to be honest with you, I got 5.9979, which, as far as I'm concerned, rounds to about 6.0 times 10 to the -14 molar hydrogen ion concentration. Hydrogen ion concentration. So they agree. They should, right? In fact, I would recommend doing both methods every time you can, just to be absolutely sure that your numbers worked out. And even multiply your hydrogen ion concentration by your hydroxide ion concentration. Make sure you come back. It will come back. This is, by the way, 1/6 times 6 times 10 to the -14. This is 10 to the -14. 0.166 is basically 1/6. So it's 1/6 times 6. So this will work out. But I'll leave that up to you to try. Okay, some more examples here. Again, you don't actually have to do any real calculating to make these kinds of comparisons. And I hope you don't. I hope you don't try to turn to calculations for this, because you really don't need to. Sometimes it's better and shows better understanding. It shows better understanding if you simply can apply principles without actually plugging numbers into formulas. So which of the following solutions has a higher pH? Careful, higher pH. What does that indicate? That indicates more basic, less acidic, lower H+ ions. Since we're dealing with acids, we're going to look at the relative number of ion concentration, lower H+ ion, actually concentrations. Same thing, but for our purposes. Okay, so let's take a look at this. This is a very tricky one, actually. And I'll be honest with you, this is kind of tricky. The reason I say that is because it's making some fine distinctions that you may or may not have the tools to actually figure out yourself. And so this is, because this is an example, I can get away with talking like this and doing stuff like this. We are comparing a diprotic acid to a monoprotic acid. Now, wait a minute, though. Here's the problem. This would be straightforward if you understood everything I said so far. This looks like it should be straightforward. There's only one problem here. There's one thing I haven't really told you yet, which is that the second deprotonation, even of a strong acid, the second deprotonation of any acid, even a strong acid, is always very weak. What does that mean? That means that we really aren't going to get 2 protons for sulfuric acid. We're going to get, for sure, or we're not going to get double the number of protons. We're definitely going to get all 0.98 molar of the first protons, but we're only going to get a small smidgen of the second set of protons. The bisulfate ion, or the hydrogen sulfate ion, is actually not going to dissociate very well because removing a second hydrogen ion is more difficult. Why is it more difficult? For reasons I've been saying all along, it's always more difficult to remove a positive thing from a negative thing because there's that mutual attraction. Removing a positive from something that is not positive but is neutral, removing a positive from something that is neutral is easier. So that first deprotonation could be strong, meaning you get 100% dissociation. You get 100% deprotonation of the first proton from sulfuric acid, from the diprotic acid sulfuric acid. But then you're left with hydrogen sulfate. Hydrogen sulfate ion is a weak acid, and you can depend on it being weakly dissociating. You're going to get less than 10%. Actually, I'll be honest with you, you're probably going to get much less than 1%. So what is the answer to this question? To be honest, I'm not even sure what the answer is. I'd have to look up the information. I'd have to look up what's called the acid dissociation constant for bisulfate or hydrogen sulfate ion. And then I'd have to do something called an icebox, which is a sort of calculation, sort of step-by-step calculation to figure out what the number of hydrogen ions actually would end up being at equilibrium when this thing finally dissociates this way to get my sulfate ion and hydrogen, free hydrogen ion. So we can compare hydrogen ion concentrations directly by noting that one is more monoprotic, the other is diprotic, except there's only one problem. Even if we get all 0.98 molar, even if we produce all 0.98 molar from the first association, that's still less than 1 molar. Is the second deprotonation enough to get us over that hump? Let's assume it depends. The answer is it depends. Let's assume, I might be saying something different from what I wrote down. Here I was making the assumption that the dissociation of that second proton was going to give you more. It was going to put you over the top. It was going to give you more than 2%. And that's true. If I assume a 10% dissociation, well, what's 10% of 0.98? That's going to be 0.098 molar. 0.098 molar of that second hydrogen plus the 0.98 of the first hydrogen ion gets us to over 1. 0.98 plus 0.098 gets us to 1.078, or about 1.08 molar. So if we assume 10% dissociation for that second deionization, that second deprotonation, then that'll actually be enough to put us over the top. If, on the other hand, it were something less than 10%, if it were, say, for example, 1%, then the hydrochloric acid would actually have the higher hydrogen ion concentration. It really depends, and I actually don't know what the number is off the top of my head. I can look it up right now, and actually so can you. And if you are very curious, the problem is these dissociation constants don't give you percentages. You would actually have to go through a fair amount of calculating, just arithmetic, but still a fair amount of calculating and understanding to convert a Ka value into an actual percentage. It's probably not worth your time right now. But I would just say that you can actually look these values up. Maybe someone has done the math for you, or you can look up the Ka value and just take an educated guess about the dissociation constant. Generally speaking, dissociation constant of about like 10 to the -3 to 10 to the -1, or pKa of 3 to 1 is probably in like the 1 to 10% range. Anyway, so basing it on this assumption, and this is just an assumption on my part, my point is not to tell you how to do this kind of problem necessarily. My point is sort of to exercise your thinking, your sort of squishy application of these principles. So if the second deprotonation, also to introduce the concept of the second and third deprotonations always being weaker than the first. So for a strong acid, the first is a strong acid is only strong with respect to its first deprotonation. So for example, sulfuric acid is a strong acid, but only with respect to producing hydrogen ion plus hydrogen sulfate ion. The second deprotonation, however, of that to produce sulfate ion, pure sulfate ion, is actually quite weak. And you have an equilibrium established. In fact, the bisulfate ion, HSO4 minus, is amphoteric, somewhat amphoteric, meaning it has a very, very weak tendency to pick up hydrogen ions, but it has a very, very weak tendency to release that last hydrogen ion as well. Actually, it's weak in both ways. So it's ever so slightly amphoteric, not to a practical level, but technically, in theory, it is. So HCl ends up having the higher pH. What does that mean? Higher pH makes it sound more acidic, but what does that really mean? Less acidic. If we assume that the second deprotonation of sulfuric acid is about 10% or more. Even 5% would still get us greater molarity of hydrogen ions. 1%, you might not actually get it. What's 1% of 0.098? Isn't that just 0.98? Isn't that just 0.0098? Why is it erasing everything I'm putting? 0.0098, yeah, that wouldn't get us there. That would still be less than 1. So, but as long as it's over about 2 or 3% dissociation for that second deprotonation, you will have more hydrogen ions in a solution of sulfuric, a 0.98 molar sulfuric acid solution than for hydrochloric acid. But again, you cannot predict what the dissociation value will be. I either have to tell you, give you a percentage, or, that's about it, actually. That's the only way. I'm not going to expect you to look it up. I'm certainly not going to give you Ka values to work with in this class. That's not what we do in this introductory chemistry class. So there you go. Okay, comparing the pH of a weak acid to a strong acid. Now, unlike the previous example, in this case, notice the concentrations are the same. This is a slam dunk. If the concentrations are the same between a weak and a strong whatever, whether it's an acid or a base, if the concentrations are the same, which one of the following solutions has a lower pH? Without a doubt, the hydrochloric acid will have a lower pH, meaning more acidic, meaning higher. Remember, don't take the word lower to mean something, the opposite of what it means. A low pH means a high acid concentration, a high hydrogen ion concentration, more acidic, lower pH equals more acidic. The strong acid at the same concentration will be more acidic and have a lower pH than the weak acid. Both are monoprotic, so we don't have to worry about multiplying protons. They both have the same concentration, so it's not like one has a high concentration, one has a low. They have the same concentration. So we don't have to multiply the concentration by any factor. We can take them as given. The only thing that distinguishes them is one is weak and one is strong. The weak one will dissociate to produce only a small percentage of hydrogen ions, hydrogen ions. By the way, it doesn't even matter what I tell you. The fact is, as long as you know it's weak, you know it's not going to give you 100% dissociation. In other words, you know that whatever the hydrogen ion concentration is, you don't have to know the number. You know that it's going to be less than HF. Whereas the hydrogen ion concentration for HCl is going to equal exactly HCl, which is still equal to HF, which is therefore greater than H plus from HF. So that's the train of logic that you follow. Just remember, lower pH means higher H plus concentration, means more acidic. Don't let the sort of terminology fool with your head. Okay. And last, and kind of least, actually, because we've already done this, I'll just briefly, I kind of already mentioned this. This is just here for your review. We've already talked about acid nomenclature, so I'm not really going to go over it here. This slide summarizes everything about acid nomenclature that you would possibly want to know for inorganic acids, which are the only kinds of acids we've looked at. We've looked at all of this. Just remember to make the distinction between oxyacids that are polyatomic ions that contain oxygen, binary acids which contain no oxygen. Use the prefix hydro for binaries. Don't use the prefix hydro for oxyacids. And make a distinction between the 8 ATE versions of the names of polyatomic ions and the ITE versions of the polyatomic ions. And that changes the endings of the acid names. Itis, atic. And over here, hydroic acid. That's it. If you remember that, you're golden as far as naming. Here's a question for you. One of our polyatomic ions was C2O4 2-. It was called the oxalate ion. So the oxalate ion, so if I have H2C2O4, what is the acid name of this acid? And it is a very common acid, by the way. It's an acid I don't particularly like. What is its acid name? I'm not going to answer this question. You get back to me if you want to know the answer. Don't look it up. Try to see if you can apply the naming rules. See if you can come up with the correct name. I bet you'll even recognize what the name is. So let me know how that goes. And let me know in general how all of this goes. If you have any questions or concerns or spot any errors, please let me know. I hope it all goes well. I hope that was informative. If you want to see any more examples of this, I'm happy to help out. If not, that's fine. We have a couple more videos. I believe I'm going to break them up into 2 more videos for buffers and titrations. You probably have already done titrations in lab or will be doing it in lab, depending on the timing of this video when you watch this video. But we'll go over that in a little bit as well. In these live videos. All right, everyone. I hope to see you in the next video, or you'll hear me. Take care, everyone.